Please take your seats. The program will begin in 5 minutes. Please take your seats. The program will begin soon. Please silence your mobile devices. Please take your seats. The show will begin momentarily.
It's a very exciting experience. So many good teams from all around the world. This is a way to be challenged and to learn things.
Are we up to the task? Can we use our existing technology, our existing expertise?
A lot of the world is going to end up having these fleets of robots. It's very exciting to see all these various and different technologies that are state-of-the-art.
The SubTv challenge for us represents everything that relates to how we can make robots to be resilient in extreme conditions.
This is kind of a step up for us, even bigger of a challenge than we faced so far.
It sells to all robotics, make sure that your robots are able to do their mission. This is absolutely difficult at the moment.
Welcome to the DARPA Subterranean Challenge Urban Circuit Award Ceremony and Technical Interchange Meeting. Please welcome to the stage SubTv Challenge Program Manager, Dr. Timothy Chung.
Oh, what'd you think? Was that amazing or what? I mean, that recap, I think, just summarizes all that energy. And I think the feeling of being superstars here is accurate. You are all superstars here at the SubTv Challenge. So it's my pleasure to welcome you to the award ceremony and the technical interchange meeting for the DARPA Subterranean Challenge Urban Circuit. I think there was so many lessons learned and so many experiences had out here that I'm so proud. I couldn't be prouder of the accomplishments and the achievements that you all have made. And in fact, it's not only the achievements, but also the failings that you all witnessed as well. These are all learning and teachable moments that I'm really proud that you have made. Some perhaps prouder than others, but in general, I'm super excited about all of the work that has gone on here. I think there have been really high moments and low moments, both literally and emotionally, and I think that's all part of what it means to be part of a DARPA Grand Challenge. So I'm really excited to welcome all of you. It's not just the systems competition, but also the virtual competition that we host here at the award ceremony. I know you're all eager to get to the award, so we'll get started here in a second. I think one of the key things that I'm really excited to talk about is some of the lessons learned that we've had since Tunnel coming into urban. I know that was a long time ago. It feels years ago, and maybe Cave feels like just tomorrow, but we're here to focus on the urban circuit, and I'm really proud of those accomplishments. I think what we've seen is that it's not just about how far you can go, but how you get there. It's not about how quickly you move, but how agile you can be when you're moving through these really complicated environments. And so I think many of you were able to demonstrate that. If nothing else, you have a lot of data that I know you're eager to get home and parse and understand even better and continue to improve the technologies. So I'm also pleased to welcome a number of distinguished visitors here. I think what they hope to take away from this interchange opportunity are the nuggets of insights that you have all gleaned during your time here in Washington State. And so I look forward to your interchange, not only in the slides that you're describing, but also in the discussions that no doubt you'll have amongst you all. So I'm looking very much forward to that. Okay. With that, I am pleased to introduce my boss's boss, my boss at DARPA, the Acting Deputy Director of Defense Advanced Research Projects Agency, Dr. Dave Honey.
Well, good morning, everybody, and thank you, Tim, for the introduction. Tim told me that all of the robots made it home safely, and also I think probably last night for many of you was the first night you were able to get a full night's sleep, in case you were so inclined to do that. But again, I want to offer my congratulations to all of you. The fact that you were willing to come to these events, to participate, is fantastic and very important to us. One of the questions that we get quite often is why are we continuing to do grand challenges? Whether it's a launch challenge or a subterranean challenge, we put them in the general category of grand challenges because, as all of you who have participated in this particular one understand, these are really amazingly complex events. They are very difficult, and so they're very worthy of the title Grand Challenge. We're coming up on the 16-year anniversary of DARPA's first Grand Challenge. And so why do we continue to do them? Is it to be able to come to places like this, to get to tour an almost finished nuclear reactor? There are some actually very important reasons why grand challenges are continue to being pursued by DARPA and why they've really, I think, caught the imagination of a lot of other R&D agencies and why they've become very popular. For me, I think the biggest reason, the thing that I most look to these grand challenges to do is to help us at the leadership level understand the current state of the art. And it's only when you get into this sort of a practical experiment where people have to solve really hard problems that you can really see what the current state of the art is. Quite often people think when I say that I'm referring to the state of the art of the hardware. But as you go around and look at all the different vehicles, and I'm assuming most of you did, you can see what we often refer to as the democratization of technology, which it means that all of you have equal access to eBay, Amazon, and all other sorts of venues, and pretty much you can get the hardware that everybody has access to. So when I say, where are we in the state of the art, it's really where are we at the state of the art in innovation, thinking, and problem solving. So that came home to me as an important attribute during the first Grand Challenge. So this is my second tour at DARPA. I was here earlier. I was there for the first two Grand Challenges. In fact, the third one was just getting launched as I departed DARPA. But I was like a member of Tim's staff at the time, that sort of thing, doing the grunt work of helping to make this kind of an event happen. And for the first Grand Challenge, it was pretty obvious to a lot of us that it was going to be one and done. We were going to do it. It was going to happen. A bunch of vehicles were going to make that road race and get it done, and that's it. We would never do anything like that again. Because at that time, if you looked around, the platforms had been around for quite some time. Automobiles had been around for like a century or so. And a lot of the sensors and a lot of the associated hardware, it was there. It was pretty easy. All you needed was the software to make it happen, and how hard could that be? Well, as it turned out, it was really hard. None of the robots made it very far. I was out somewhere in the middle of the course. We saw nothing because none of the robots made it very far down the road at all. I think some caught on fire, others crashed. It was not a good day. And it clearly showed that innovation and thinking and problem solving for autonomy was really not where it needed to be. In fact, I think a lot of us, me included, have made the mistake of assuming since we saw automation and where it was, that meant that autonomy was a slam dunk, and it isn't. And I think, the challenge courses that Tim has put together in this particular Grand Challenge really shows and separates out, the different levels of innovation thinking that is going on. So from my perspective, this is really what we get out of the Grand Challenges, and I saw it really taken to a very high level in this one, and I know that in the remaining parts of this, we'll see that as well. Something else that I would like to point out, another reason why it's so important to really take a look at that aspect of these challenge events. Nobody has a monopoly on innovation and problem solving and innovative thinking. So going to the next Grand Challenge that I participated in, Grand Challenge number 2, wasn't really that much longer after the first one. The community really came together, thought through the problem space, and came up with ways to solve it. Roughly a half a dozen vehicles made it through, and as some of you who followed that one know, Stanford won, Carnegie Mellon did very well. There were others, Oshkosh had its big truck, they did, people that you would expect to do it. But there was another participant that didn't get as much attention, but it was the one that for a lot of us was really interesting to see. There was a mom and pop insurance company, and their company was down in New Orleans, and they entered as one of the contestants, and they made it through the trials and whatnot. And then we lost contact with them because Hurricane Katrina swept through their area, and we didn't know where they were or whether they were going to make it or not. And it turned out, again, small company, literally a mom and pop insurance company. They had some folks who were, I guess, gearheads and others who were into programming and decided to enter this race. And they did show up, and they did enter, and theirs was one of the vehicles that made it through. And what was interesting to us was when we were looking at the post-analysis of the event, we believed that if their algorithm had just been a little bit more aggressive on the flat parts of the course, they would have outperformed Stanford, Carnegie, Oshkosh, and everybody else. But again, they didn't have probably enough time to tailor their algorithm development, and so they came in where they came in. But the point is, you never know who is going to come forward and have the innovative idea, the innovative strategy that is going to make a difference. It doesn't necessarily mean that you've got access to all this talent or all these resources. When we have this kind of, again, democratization of technology, it really levels the playing field, and it opens up to those who really want to be creative. As I mentioned, this is actually my second tour at DARPA. I was there for quite a while and then came back. And one of the things that I've learned is that technology surprise happens every day. I never know who's going to come through the door with an idea that we didn't think of, and it will be something important that will change things dramatically for us. And so I encourage you all, as you go forward, to be open-minded on new technological approaches, but also look for opportunities such as this to participate in. And at some point, especially for a lot of you that are here, you'll be graduating, moving on, running research groups, maybe working in funding agencies and whatnot. Do look for opportunities to support this kind of work, because again, what you'll learn out of it will really startle you, and you will experience technological surprise in that environment. I want to close by thanking Tim, thanking his staff, also thanking the Tactical Technology Office, Tom Beutner, Mike Leahy, the leaders of that office, who this week have not just this challenge going on, but one up in Kodiak, Alaska, where they're trying to launch a rocket. It's a very busy office and very busy place. But one of the things that I would like to leave you the thought with is that at DARPA, our technical staff typically does about a 4-year tour and then moves on. We're the only agency I know of that does that, where every year we fire a quarter of our best performers and send them on their way, and then bring in more. But it's because of that rotation that we're able to bring people in with innovative ideas that we hadn't thought of, who want to tackle hard problems and create their own grand challenges. So for those of you that are able, I hope at some point that you will think about maybe a tour at DARPA, talk to Tim, talk to Tom, let us know. We'd be happy to talk to you about what it's like to be in an agency that does these kind of things. But again, my congratulations to all of you for a very successful event. All robots recovered, no injuries. That's that's an important thing. Again, I know that all of you learned a lot. We learned a lot. And I thank all of you for making this happen today. Thank you.
Great, thank you very much, Dr. Honey. I think the whole message here is that the legacy of these DARPA Grand Challenges is something that we take great pride in, and I hope that you all do as well. I think there's a great tradition there that we are embarking on here today. So without further ado, I'm excited to get to the awards presentation section of our program this morning. We're going to start off first with the virtual competition. I'll highlight a number of notable mentions through our superlatives. I'll mention then announce our top place winners, and then we'll award our prizes as well. So for those of you, as we go through our superlatives, I ask that you stand to be recognized at your seats. For those of you who will be recognized as our top place and prize winners, I'll ask that your whole team comes up to the stage so you can be recognized by all of us. Okay, so for the virtual competition, the way this was constructed, for many of you who may not be fully aware, is that this is a chance to explore a lot of the subterranean challenge problems in simulated context. And what that allows us to do is really push and stretch and scale to the types of problems that we really want to face in the real world. And so in this context, we had numerous competitors, 8 competitors from all over the world, who are able to generate their autonomy and perception solutions in essentially Docker containers and submit those to our SubT cloud infrastructure and get those evaluated. And we did so across, for the first time revealed, these 8 competition worlds. So we've fabricated these competition worlds out of a number of different tiles. They represent everything that you have seen in that SAP center, where you have verticality, elevator shafts, stairs, big open areas, a lot of obstacles. And you also see a number of other facets, including things like subway tunnels and rails and things of that nature. This gives us that chance to go and explore in that synthetic environment some of those problem spaces. And so some of our challenge environments here really stress things like lots of different levels, how do you deal with long traversals in identically looking tunnel systems, and these are the types of problems that we're deeply interested in being able to exercise. And so with that, let me go to our superlatives. I'm pleased to announce that Barks was able to achieve the most accurate artifact within the SubT simulator. Please stand. Barks, yeah, joining us. Thank you. And so in this case, they were able to navigate this particular world, rather complex as you might imagine. It has a staging area, just like in the systems competition, and they had to navigate all throughout the space to be able to find this vent within 20 centimeters. So that's quite the accomplishment with all of the error and uncertainty that they face and that we model in the SubT simulator as well. Our next superlative goes to the most traveled robot team, Team Colembala, who's joining us remotely. In this case, they were able to collectively, between their 3 robot ground vehicles, traverse nearly 11.5 kilometers all throughout this particular course, which you can see all the traversals maneuvering through. This goes all the way across ramps, different levels, etc., which is pretty remarkable. Okay. Our next superlative goes to most levels traversed, which is very relevant here for the urban circuit, and that goes to coordinated robotics. Coordinated, could you please stand, Kevin? Yeah, there you go. So in this case, he was able to traverse 19 levels and keep on going. He had 4 of these quad rotors flying up, through, around, over a lot of the different features that make urban environments really challenging. So congratulations to Kevin as well. Okay, so the 4th superlative goes to quickest artifact report. This is the quickest achievement, and that goes to our team who's joining us remotely, the Flying Fitches. they were able to identify, maneuver, and fly, and within their first 2 minutes be able to find this cell phone, which, at least from the simulator view, really hard to find, right? And so we actually had to call it out for you all. So congratulations to Team Flying Fitches joining us from Germany. Thank you. So I'm pleased to now announce the top place winners of the virtual competition. I'll ask that the teams join us up on stage as available. So going with our third place, Robotica, please come to the stage. Congratulations. Yeah. Thank you. Yeah, please, let's get a picture taken here. Yeah, anyway. Multiple levels. Yeah, please, we'll take a picture here. Welcome, congratulations. Pass this to you. Oh, let me get in front. There you go. I'll pass this to you guys. Congratulations. Yeah, get your picture taken. Other way. Congratulations from teacher.
Thank you. Thank you.
For our second place winners of the virtual competition for the urban circuit, that goes to Coordinated Robotics. Please come on up, Kevin. Great job, Kevin. Yeah, congratulations. Here you go.
Hold your breath.
And that was great. And for our first place winner, let's welcome Barks to the stage, if you would. Congratulations, Barks. Congratulations.
Thank you so
Yeah, that's
much.
very exciting. Yep. Congratulations, Team Barks from MTU, Michigan Tech. Okay. Great job, everyone. Okay, on to our prize awards for our first place, which will receive a $100,000 prize award, goes to, let's go that way, to the Flying Fitches, who are joining us remotely from Germany. Congratulations to the Flying Fitches. Not my tech, but thank you, Margaret. I'm sure they are very excited watching the YouTube feed right now that's currently live. Okay, for our next prize winner of $150,000 goes to Team Robotica. Please come to the stage and be recognized. You can hold it. There you go. All right, congratulations. And you can take that with you. No, take it, take it. It's yours. And for the final top prize winner of $250,000 for our virtual competition for the urban circuit goes to Coordinated Robotics. Kevin. There you go, Kevin. Here, I'll let you hold it as well. Here you go. Yeah. Awesome. Fantastic work. Congratulations to all of our competitors and certainly to all of our winners. It just goes to show you that there's a lot of innovation to be found and you never know which corner you can find it. So I think that's fantastic, and I'm very proud of the accomplishments on the virtual competition. At this point, I'm happy to show you the results of the virtual competition, those 8 worlds that teams were able to tackle and go and see ways to find across many, many runs. This is in the context of a simulation that you're able to really study and understand the problems in the virtual environment that allow you to translate that hopefully to systems environments as well. So let's get to the systems competition. I'm really pleased to announce our first round of superlatives associated with the systems competition. In the context of, let me just paint the picture of the courses. Many of you saw SatSop. The course walking tour hopefully was very illuminating for many of you, or interesting at the least in terms of what you were able to see. And so just to tell the story of how far we've come just in 6 months since the tunnel circuit, this is the ground truth point cloud map for the SatSop Center, just from a bird's eye view. And this is what you all face for those of you who competed in the tunnel circuit. And this is to highlight the differences in the scales and the structure of the environments that you're tackling with these subterranean technologies. So again, it's not only about distance, it's not only about diversity, it's also about density and the understanding of how difficult these types of environments are and how you push the types of technologies that you're developing. Some of the things that we saw on the teams, just to highlight. Here are some of the opportunities that you all as teams were able to go and explore through all across the different levels that you faced on alpha and beta courses. These are the first 5 teams on alpha course. Here are some course maps from beta course, and the diversity of the maps that we're seeing and the quality and just kind of the comprehensiveness of those maps really speaks to not only how important those technologies are for being able to map these environments, but also how you translate that into actionable situational awareness to be able to report those artifact locations precisely. Okay. So the first superlative goes to Team Cerberus. If you wouldn't mind standing in place to be recognized. I know you're excited about this. Here, Team Cerberus was able to achieve within 30 centimeters of this backpack. We're all cheering for you for sure. Wanted to recognize all of that hard work. Congratulations, Team Cerberus. So close. Our most accurate artifact report goes to Team Cyro Data 61. Where are you, Cyro Data 61? Stand in place. Recognize. Awesome. And so they were able to submit this artifact report and get to within 22 centimeters of the actual ground truth that we've captured here for this backpack. You may have seen that on your course walking tours as well. Our next superlative goes to the down to the wire report. This is the recognized as a team that was just able to get it right before the buzzer, and that goes to Team Explorer. Where are you guys? Team Explorer? Stand. You had us at the edge of our seats as the buzzer was counting down, and within less than 24 seconds to go, you were able to get that significant point at the end, so I wanted to recognize that. And that was a gas artifact, which is pretty phenomenal as well. We wanted to highlight the most improved mapping. This is going to the team that showed map at their first run, going to the map on their second run, or to their fourth run, and we're able to highlight quite an improvement. Coordinated robotics, please stand with your whole team. And this is absolutely noteworthy to see how you went from your first time on beta course all the way to that last round on beta course. Very impressive. Good job, everyone. Thank you. And then finally, I wanted to recognize this nugget, which spans both the systems and the virtual competition, but the best virtual to reality award goes to the team that was able to take insights from that SubT simulator in our virtual competition, mash it around a little bit, merge it into their systems platform codes, and really take advantage of the lessons learned from that virtual competition into the systems competition goes to Team Robotica. Thank you, Team Robotica. Please stand. Great. All right. So I'm pleased to announce the top place finishers of our systems competition for the DARPA Subterranean Challenge Urban Circuit. Starting with third place, we have Team CTU Krasnor. Please come on up. Pass this to you. Congratulations. Thank you. Thank you. Please get you. Congratulations, everyone. Congratulations. Congrats. Congratulations. Good job. Let's give them a round of applause. Great. Thank you very much, CTU Krasnor Lab. Taking home that second place position for the systems competition is Team Explorer. Please come to the stage. Got a big team, make room. There you go. Sir. Congratulations.
Thank you.
Yep. Hey, one. Great, congratulations, everyone. Yeah, congrats. And to announce our first place winners of the DARPA Subterranean Challenge Systems Competition for the Urban Circuit goes to Team CoStar. Congratulations, team. Come on up, everyone. Come on in. Welcome, everybody. There you go, Ali. Let me present this to you. Congratulations. Yeah, congrats. Congrats to your whole team. Great job, guys. Congratulations on your accomplishments. Thank you. Congratulations. So for our prize winners for the Systems Competition Urban Circuit, I'm pleased to announce that the winner of the $250,000 prize goes to Team Coordinated Robotics. Welcome to the stage, everyone. There you go. Congratulations. Congratulations, everyone. Fantastic. You get to hold a check. If I knew as a sophomore in college I could have the opportunity to join something as big and as amazing as this, I think this is kudos to Team Coordinated Robotics. to be able to offer these types of opportunities and accomplish so much. And for our $500,000 prize, going to the winner here for this top prize goes to CTU Crass Norlab. Welcome, congratulations. Congratulations, congratulations. There you go. Here, please. Welcome, welcome. All right. Congratulations. Congratulations so much. Congratulations to all of us. I think we really have this opportunity to celebrate all of the accomplishments, all the lessons learned that we're all taking away with us. Really big congratulations to, of course, our prize and top place finishers, but broadly, I think there's a lot of opportunities for us to continue to celebrate each and every one of our respective accomplishments. So congratulations, everybody. And with that, I'm pleased to welcome Captain Jimmy Walker. Oh, actually, I'm going to show you the leaderboard first. We all saw this, but I want to highlight here that this was a pitched race to the top, and I'm really pleased to see the continued progress and growth of the technologies to allow us to achieve this great opportunity to showcase the technologies that you're building out. Thank you, everybody. Okay. So let me please introduce Captain Jimmy Walker, who's joining us from the Seattle Fire Department. In the context of the urban circuit, we're deeply interested in those problem sets that our first responders and warfighters face in these complex underground environments. And so with that, Captain Jimmy Walker.
Thank you. Before I get into my presentation here, I'd like to let's give a round of applause for everybody that has traveled from very far away, put in thousands and thousands of hours to not only make the competition happen, but to compete and in some cases win some very nice prizes. So let's give everyone a round of applause. So I'm here representing the first responder community, and I have a challenge for you, because one of our biggest challenges in the first responder community is, how do we manage what we can't see? And I'm going to come back to this in the presentation and take a little deeper dive into that. So I'll share a little bit about myself. I've been in the first responder community for about 25 years, and I've had some incredible opportunities where I've been able to be part of small teams and bigger teams that have really made an impact, both here locally, in the region, on a national level, responding to problems here, and also on a pretty big, large-scale disaster level. One of those things is I also represent within our fire department. We too, much like the military, we have small special operations communities. And that's what kind of brings me here today. When I first got asked to come down here, I had very little information on, of course I knew what DARPA was, but I didn't really know. And I certainly didn't know much about what this Subterranean challenge was. And I have to say there's some parallels within the first responder community that I recognize immediately, and some of them are some intangibles, where I heard some stories when we got to visit the teams where they talked about maybe a team's robot got stuck in customs, maybe something broke and they didn't have spare parts. Well, guess what happened? They shared their information, they shared some of their spare parts, some of their technology. And that really struck a chord with me because that's exactly what it's like in my line of work. The other thing was, I was really taken back by just the worldwide. There's people in this room from all over this world, and I was really taken aback that everybody came together in tiny Elma, Washington here in the United States. There was one other thing that really struck me, was I think there was at least 2 teams that I was made aware of that reached out to the schools. Now I know maybe one of their intents was to have somewhere to work on their robots because nobody wanted to work in 30-degree weather in an old nuclear facility. But one of the things I appreciated was that you're reaching back to the community, even in this small rural community here in Elma, Washington. And that, talking to what the director was talking about, the deputy director, they're the future. They might be walking into the DARPA office with future ideas. And they come from very small communities. And I'm sure there's some people here in this room that worldwide you too come from very small communities. So I'd like to thank you for that. And actually, who are the teams that reached out to the schools? Are they here? And can you stand up? Let's give them a round of applause. I think that's going the extra mile. Thank you. Okay, so the community that I serve is the city of Seattle. It's anywhere between 1 and 2 million people, not unlike any other large urban city throughout the world. And it has a lot of the same challenges that large urban cities have. You can see that we have quite a bit of waterfront, and there's a lot of things like tunnels under that waterfront. We have mass transit systems. We have high-rise buildings. We have all of the challenges that go along with the subterranean environment that Tim and his group is trying to bring out some of this technology. But one of the unique things about Seattle that you'll notice here in one of the photos is this black and white photo. That's the city in 1889 when it burned down. So not only do we have the standard challenges of the subterranean environment in the city, but we actually have a part of our city that is built on the old city. So that in itself brings some additional challenges. So, when I first came out, like I said, I didn't have a lot of information or background, but I'll tell you, I was legitimately blown away by some of this technology that some of it I knew about, some of it I didn't even know existed. And so some of that technology, back to that slide of how do we manage what we cannot see, I was familiar with the LiDAR technology, but not to the extent that I saw you using it. Some of the remote gas detection pieces, and one of the pieces that I'll challenge you to as well is not just the gases, but think about detection of radiation and the challenges that could bring. The big piece for us is we're humans. We're sent downrange to solve problems, and we really like to do that. However, we do recognize that there are some hazards that they're just too big for us, and we need help with that. And so being able to remotely identify some of these hazards, that's a critical piece to our first responder community. And back to again, tying back to the how do we manage what we cannot see, is getting that real-time intel, watching the competitors in their home base or at their what we would call a command post, and just managing all of that. And I'll touch on this. I have some experiences out at that facility as well that I'll touch on in just a second. Where I see the real value here is unifying these elements together, where you were challenged to use your technology and go about your competition. Where I see the value in this is bringing more of the human side into it as well, and combining those together and really being able to solve some of these problems downrange. The bottom line is right on the bottom of the slide here. This is what is really, really important in our community. Increasing our operational tempo, that can save lives. That can really make a difference. The other piece for the people that are sitting up at their home base or in their command post that are at kind of the top of the food chain, they're very concerned about how much risk we're taking, and really we're able to mitigate the risk in some ways by better intel. And that's what I see the value in your technology. So, I've had the experience of probably conducting and operating in that building that you guys conducted your exercise probably 20 times. And I can tell you that I get lost just as easily the first time as the 20th time, because as you can see in some of these photos, we can't see, right? Our vision is obstructed by smoke, darkness, things like that. One of the things that I heard some of the teams talk about was their limitations on their drones, for example. Like I heard some fly times of 10 minutes, 12 minutes, things like that. Well, our limitations are, in this case, being in an IDLH environment, is wearing things that keep us from breathing the bad air. So there's some major limitations with that. In this case, in one of these photos, we're wearing some rebreathers where we rebreathe our own air. And in theory, we could last up to 4 hours. However, we are human, and we can only last so long. So in theory, maybe you get a 2-hour operational period out of us. You guys have the same challenges with your battery life. I thought that was an interesting parallel. The biggest one, and it's so funny because it's the same, was the comm links. Every time we've done exercises out here, we've lost comms. We know we're going to lose comms. Just like I heard you talk about, you're going to lose comms. I was really impressed with how you were solving those problems in a much more simpler way than it seems we are. And so I'm interested to take a deeper dive into that and see what can be done. And I did have to chuckle how many times I heard the word autonomy, and then somebody amongst one of the teams said, well, basically, I know we're going to lose comms, and hopefully they come back, meaning the robot. Well, I can tell you from experience, that's exactly how it is in our world as well, where we have an incident commander, they send us down below, we lose comms, and they hope we come back. So it's interesting that we share some of the same challenges. And so, like I said, I am interested in taking a deeper dive and seeing how can we partner in this and improve things on our side. Just a quick example. Our technology in Seattle obviously is nowhere near where this room is at. But we have a little bit where, as an example, one of our missions is we do have to go under the water into those subterranean environments as well. And some of that, again, we're limited by human factors. So we do have some remote operated tethered vehicles that we use. And again, the technology, it's usually black water. You can't see. So it's things like the side scan sonar and the video feeds. So we are somewhat exposed to some of this technology. So in closing, this right here I think is critical. The role that DARPA has taken on bringing these different communities together is really what's going to make changes. That's what's going to bring things to this next level. And I do think it's crucial to our future. Thank you.
Thank you, Captain Walker. I think it's so important for us as technologists and researchers to recognize that there's so much more to the robots we build, to the comms link we try to use, to the maps that we create. I think Captain Walker's mission sets and those that we're really trying to help improve through the technologies that we're developing, being able to incorporate that, I think, is critical. So one of the things I'll highlight, he left his email address at the bottom there. Reach out to first responder communities and others to really get that insight that will help drive your technologies. And who knows, it could be the thing that makes your technology dominate all others later on. Okay, so we're at the point now we can take a short break. We'll be reconvening here shortly after this break at 10:30. We'll commence the technical interchange meeting. I encourage you to interact with your fellow competitors. We have some displays in the back if you haven't seen. Those are the original blueprints of the SATSOP reactor facilities. Take a look and see all the nooks and crannies, some of which you may have seen and perhaps many that you did not, as well as some of the other interactive devices we have out there. See you back at 10:30. Thank you, everyone.
Please take your seats. The program will resume in 5 minutes. Please take your seats. The program will resume soon. Please take your seats. The program will resume momentarily. Please welcome back SubT Challenge Program Manager, Dr. Timothy Chung.
Great, welcome back everyone, and I'm pleased to get the technical interchange meeting off and running. This is an opportunity for teams to share the knowledge and the insights that they've learned throughout both their virtual experience or their systems experiences here at the Urban Circuit. So the way this will work is that we have opportunities for speakers to come up to the stage or present remotely and have 15 minutes to be able to share those insights. We have microphones scattered throughout this floor as well. I ask that you ask your questions during those open question periods in those microphones so that our users who are viewing via the YouTube feed can also hear your questions as well. And so again, there's a timer right here. You have 15 minutes, and in that, I look forward to a lot of those insights and nuggets of lessons learned. First up, we have our newcomers to the SubT Challenge, who I'm really pleased to welcome. So that's NUS SEDS coming from National University of Singapore. Welcome.
So good morning, everyone. So I'm Arjo from Team NUS SEDS. We're basically about 11 undergrads from the National University of Singapore, and we decided to enter this challenge. We were given a small amount of seed funding to experiment around, with which we have come this far. And we're relatively a flat organization, so it consists, where's the clicker? Is this the clicker? Okay, cool. All right, so we are looking at, so the few things we realized is that urban areas have tight passageways, narrow spaces, so we were looking for small robots, nothing too big, so the key was, and the spec we placed was 1R. I think the communication, we established this LoRa mesh communication network. Okay, that should read 500, not 50, my bad. So what we do is we try to compress all the data we're getting from the robots. Rather than try to pump back, try to improve on the network itself, we're trying to reduce the data size that we're sending back. So we actually compress all our laser data and to a very, very small packet, I think around about less than 100 bytes for a single piece of laser data to be sent back. Our movement and exploration is fully autonomous. So we want to relieve the network of any real-time requirements. So if you have teleoperation, you need to have some type of real-time feedback. So the idea is to remove that. And the robots themselves carry dropper nodes. So when they lose line of sight, they drop off one. We actually can use RSSI to sort of as an indicator that, hey, my RSSI is going off. Time for me to, well, leave a breadcrumb behind. So this was the original plan. Sadly, the big guy, the tracked vehicle, did not make it here in time for it, so we couldn't really climb stairs. We have some relatively redundant exploratory vehicles. These guys are not very capable. They're just, and so what really happened was, so that got stuck in customs. 2 of those vehicles actually died, and because of the coronavirus outbreak in China, we were unable to replace the PCs in time. So we only had 2 vehicles operational, sadly, when we got here. And the other thing about the Crazy Fly was unfortunately we had some control issues which we were not able to sort out in time for the challenge. So this is, wait, is this a repeat slide? Yeah, okay, sorry, my bad. So the idea is each robot is aware of a rough estimate of its state. So to prevent similar behaviors between robots so they don't go through the same frontiers, we sort of score each. So it's a frontier exploration. We score each frontier differently for different robots. So some robots will initially choose the left frontier more than the other frontiers. That way we sort of, so that it's no need to have the robots actually communicate with each other. They sort of know their own task beforehand. So the frontier exploration is sort of like there's a frontier, but we also have this thing where we choose walls. So, and if the robot gets stuck, we sort of send a random goal to recover from it. Did not work because this resulted in an oscillatory behavior very early on. Yeah, and as I said, we compress telemetry data, so we send only 2D local map. And then we just let the base station optimize for the map. All right. It's here. Is this? All right, I think that's all I have.
So what would you do differently if you came back again next time?
So probably what we would be doing, we'd be doing a lot of things very differently. So one of the things we're looking at probably is having the option of teleoperation, which we actually did not consider initially at all. So we thought, because we believed that this was an environment, so we would probably be focusing more on improving our network latency so that we can actually teleoperate from a distance, which is something we were not prepared for this time. All right, thank you.
Please welcome from the systems competition, Robotica.
Okay, hello everybody. I am Martin Dlouhý, the team lead for Robotica. I would like to convince you to remember us as a team who is trying to compete in both virtual and system track. Our team is, we have several, oh, here's great, sorry. We have several organizations involved, where one is the Robotica International, planned a startup with self-drive anything. Robotica CZ is a Czech website about robotics, around 20 years old now. University of Life Science in Prague, which is our partner developing field robots, and newly created Center for Field Robotics as a part of the university, and Cogito Team Lab, which you may have seen in a tunnel in Pittsburgh, the Freya, if some of you remember. And so what you have seen is actually software developed primarily for the virtual, or both. So in virtual and in system track, we deployed 5 ground vehicles. They were quite different in virtual compared to what you see here. Counting from the bottom up is the oldest Eduro, which is like 10 years old. Then there is a Maria, which is like 3 months old. Then there is a Clawback K3 with the 6 wheels, which is like 3 months old too. And then there is a Clawback K2, which is like half a year old, and you have seen it already in Pittsburgh. So that's like our base. Like I was like trying to, like what is our team different to all your like unexceptional teams like the winners and others, or what I'm proud of on our team, like, and it is actually the progress we did for the last year. Because today we have like 3 students from the university, which a year ago didn't know anything about robotics, and they participate in competition Robot Go Straight. It's in PSEC, it's every year, and the task is to go 314 meters straight. Easy, right? It's not. if you try to do it autonomously, you realize that gyros go off, compass is also like on a high voltage, is twisted, etc. So like these students tried in May 2019, just like the crowbar K1, they fixed the articulated joint just to go straight. Year after, here, they participate in the like world top teams with the crowbar K2 and K3, which is like next and next generation. So like, yeah, I would not imagine like faster career in my life. So like, that's what I would like to thank them. And sorry. Now, maybe these are like the slides from from the Pittsburgh. So basically, it remains the same. Like, critical is the symmetry of the robot. So like, whenever you get stuck, you can like back up, virtually flip the front and rear. It's important for us to be able to carry the robots by plane. So they have to fit in the check-in luggage, which, if you imagine the K3, it's no longer like single luggage, but 3 bags, which turned out to be like issue with Air France because we didn't get 2 bags, and it means we didn't get the wheels, which does matter. So I had some like nice videos how the guys managed to do it on Tuesday within half an hour, like to build up the crowbar K3 before we check in, which like, it will be on YouTube, but it's just like advertisement. What else? And the software, we are trying to run both on virtual and system track. So basically, we are analyzing the log files, and it should not matter if it was, like, we don't recognize the words, I would say. Lessons learned. There were like a couple of them, or many, I would say, where, like, what was the first one? I don't know, like, if you follow our first day, it was really, really bad. But it was clear that the robots are autonomous. Like, one was hitting the wall, another was hitting the barriers, but it was hitting because the lidars, which are 2D, were just like a few centimeters above them, so like it opened, so like they went there. And if you see the K3 with the 6 wheels, it wasn't a problem, so it just drove inside the barrier. Luckily for me, I could see the artifact just like behind the barrier, and that's how we scored the first point. So that's the beginning. The night after, guys said, there is no way, let's do something about it. They plug in the 3D RGBD camera, which was tested on like the smaller robots, the Mobos, and modify the Eduro so it can see really 3D to see the barriers next time. And I think in the beta, it was okay until we lost communication and like the ROS messages or ROS part failed due to some naming and local networks, again, details. But other robots just made it fine. But the third, is it time I have or remain it? The third run was like really experience. I was curious if it's DARPA who is just like pushing on us to like make sure we are doing right, because we could not talk to our robots, which were 2 meters from us. Like, it was really a nightmare for me. 1 minute before the start, I lose all terminals. I could not talk to the robot. And what we did at the end, like the last run, K2, was ask Jakub to just start the robot by the cable, which we didn't have long enough cable. And the robot went there, went back, was offline. He gave me the flash drive, and I like analyzed the data from the flash drive. So like, it was like extreme experience for me. Unpleasant, I must say. Then some experience we did with the IMUs. At some point in the tunnel, there was a place when the IMU said the orientation is no longer valid. And since that time, everything was like invalid. So like, if you lose an orientation, you know, like it does matter. Compare So like what we could do, we could recover the position from the real sense tracking cameras. Again, another lessons learned was they work fine, but make sure they don't see the robot itself, because like on the Eduro, where it was like retrofit to this robot, it could see small parts of the lidars, which if you do the image analysis are the points which are like most stable. So like although the Eduro in the last alpha course went there and back, it actually on the tracker camera looked like it's just like turning around, not moving. So that was another hard lesson learned. And yeah, as I don't have much time, I will just let you know, like if you are interested, we are like publicly we have like a regular blog where we write what we do and like what is failing, like you can laugh at us. Also on the YouTube. There is also GitHub open source, so like you can see like what we did, what we changed, if it's working or not. It's especially interesting for virtual. All you have to do to participate in virtual, clone our GitHub, build the Docker, submit it, and you can get third place. And what else? Yeah, maybe the robots, they are based on like the hoverboard motors, the BLDC motors, which you can buy like off the shelf. They are very strong, so actually like the K3 robot, the 6 wheels, can carry 3 people if necessary. And the idea was really to climb up and down the stairs, but next time. Okay, I think I'm like out of the time now, so if you have any question, I would be happy to answer. No questions.
Thanks very much.
Thank you.
And now, a presentation from UNO.
Hello, this is Vinayak Kankanwadi. I'm representing Team UNO. Team UNO is based in Brisbane, Australia. I work on the virtual circuits of the DARPA Subterranean Challenge, as well as I work full-time as a software engineer in autonomous systems. Approach was to make use of UGV as well as UAV. From our previous circuit, we wanted to improve our robot navigation. We started using custom frontier exploration for navigation. However, we had challenges in UAV as they were not stable. Main problems were on the UGV when there were slopes or obstacles. You couldn't use the LiDAR to identify any one of them. So perception challenges due to their sensor location. Identifying artifacts was simple enough and was done using image thresholding. Cartography SLAM and move base was used basically to get back to base feature. The key was you could solve the problem with specialized behavior for each circuit, but making it a generalized solution across the circuit was where most of the time was spent. Thank you for listening to me.
Please welcome to the stage NCTU.
Hi everyone, I'm Chenlong Lu, and people basically call me Eric. We are a team in CTU, so basically we are a combination of 2 great universities in Taiwan and our industrial partner, K-Base Technology. And below are our sponsor, and really happy to see them on more than the last event. Okay. And so, as I just said, we are two university and an industrial company. And we based in Hsinchu, Taiwan. There's a biggest science park just where we located. And below is our website, Twitter, Instagram. You are welcome to follow them. So, speaking to our technological approach, so for our ground vehicle Husky, basically this time we train and deep reinforcement learning agents that's doing infinite navigations. So we using LiDAR as input, and we output the control velocities and angular velocity, of course. The cool part is that we train them in a simulation environment, and in general, I would say it generalizes really well to the real environment. As in our testing environment, we can have no collision during a 60 minutes runs. And another cool part is that we want to start trying to solve the situations that the robots may encounter in particles or fogs. So we also try to use millimeter wave radar as the input of the train policy, and it still works. And for our UAV ducky float, our approach that we try to generalize the policy from the Husky to these kind of UAV robots. So the ducky float, they are not capable of using LiDAR, such a heavy-weighted sensor comparing to others. So we use millimeter wave as the input for the UGV. So we use the train policy on these UAV stuff, and it's quite, compared to the last version, we only used one RGBD camera. These millimeter wave and the train policy really help the ducky floats traversing through the course, especially I would say the round 3 of the course. We have two ducky float and one only with RGBD and one with millimeter wave, and we can see that the one with a millimeter wave radar traverses a longer distance than the one without. And come to our communication approach, and we design cool stuff. We called it ultra wide bandwidth sound communication anchor nodes, and they have two purposes. So one is that we want to create some kind of landmark inside the environment. So we use there. You can see there's a speaker on them, and we also have a ultra wide bandwidth module on them. So by localizing a sound, we have the bearing factor and we have the ranging factor from the UWB modules, and then we create a landmark. So that's the idea of the anchor nodes. And another part is the communication stuff. So we have, besides the P2P GLORA module, we have Wi-Fi mesh network and XP mesh networks. So finally come to the part of artifact detection. So this time we have really a customized model. We called it FCN pixel to pixel classification. So as you can see in the image, so the traditional FCN, the model generates a lot of noises. You can see the third picture, the FCN. You can see there's a lot of noise inside the output image. And what we do is that we add a GAN network after the FCN, so that the GAN can kind of join the real part inside these FCN images and then create a better mask from the original input image. So that's cool. And by showing this image, I also want to appreciate this challenge, because this data actually comes from Team Pluto, from the tunnel events. This is a public data set, and we really appreciate this challenge that we all team can come to something, and we can share our resources, share our experience, and we can grow upon others' experience. So finally, some lesson learned. We actually have some list here. So the first part is about the autonomy. So our reinforcement learning infinite navigation stuff, we'll say it worked well. It could traverse through the course. But the thing we encounter is our robot stuff, because of the piles of rocks, etc. So that's probably a mobility issue that our team must solve in the future. And and another thing I want to bring out in the face of autonomy is that, so after yesterday's tour, there's a thing that I think I need to remind myself as well, is that this is DARPA Subterranean challenge, but not DARPA how long you can travel challenge. So besides just doing making an agent that could travel for a long distance, our robots must have a level of intelligence that they could really go in searching somewhere that artifact might hide in some really tricky places. The second part comes to communications. So Wi-Fi mesh network, we think that there are basic communication infrastructure. However, that we probably will not rely on them too much, and that's highly relative to the level of autonomy. So our Wi-Fi, they decay in such environments, and so that's what the situation must solve with the level of autonomy, we'll say. And another thing is that we build the XP mesh network, and we'll say that they are reliable, and we'll probably take more advantage of them in the next event. So third part is the DocuFloat. So beside the navigation part which I just mentioned, so we say that the shrinking the size of DocuFloat is a right way to go, and we really found a new possibility of doing so. So we will keep going that, and that will be a characteristic of DocuFloat that we'll do in the future. And also the millimeter wave radar is really good as well. So that will be another thing that the DocuFloat would keep developing on. So the fourth part is it's about during the setup time. So from the previous tunnel circuit, we really So from previous tunnel circuits, we always spend like really amount of time preparing the robots. So in this event, we have some strategy, and also there's some engineering trick behind that, so that we can set up our robots and base station in just less than 15 minutes, which really gives us a huge benefits that although we encountering some battery problem or hardware problem that we really need to like change the stuff during the setup time, but we still have enough time to do navigation. So that's a thing that it's really doing well. And the last point, some overall preparation. So that's probably some from me, some from my professors. So first of all, the unknown environments, the challenge is about unknown environments and really in a short time. And so it's really not that easy. And also for us, it's so to test the robots, to test our systems, it's not easy to find a good practice field that our team must face in the future as well. And also so we have, of course, we have limited resources. Sometimes we have to really doing the right choice to put our resource on the right place so that we can have a right development. So that's a thing that we keep learning and keep fixing the direction, of course. And also another problem, another thing about our teams is that, so basically we are a combination of students, and students comes and go. So people come, but people graduate as well. And how we can transfer the experiment, how can we keep having these stuff to the next generation of students is another issue that our team must solve in the future. Okay, so that's all our lesson learned. And before finish, I would really like to thank our team. They are great. They do a lot of stuff. They are helpful, no matter in which year of the university or in a graduate. And also I'd like to thank another team lead who is the lead of our lab and my mentor in my master's degree as well, Professor Shea Chen Wang. I really like to thank him for his support, especially financially. And that's all. Thank you. I'm welcome to your problem.
Okay, so could you be more specific about the mobility problems? Because you mentioned on your slides that you had no collision problems, so that means that your exploration algorithms worked well. And then you said that some mobility problems. And actually, I wanted to ask, what happened? I mean, your approach sounds reasonably, actually quite heavy, a lot of sensors on the Husky. So something obviously went not as expected. So what was the major problem?
Sure, that's a good question. So what we do on the reinforcement learning is that we train them in the environment. So actually we train them in the cave environment from the part, the release of the simulations. And so we train them. So we test them in a basement of a building, and they really work well there. And in the course, so actually in all the 4 runs, our Husky stops because of the piles or the rocks on the floor. They just bump into them and stuck on them. So I would probably break down into 2 things. Is that first, these reinforcement learning agents, they still have a problem with low level or just a little height, like little piles that they're only like 10 centimeters or 20 centimeters that the robots might ignore throughout the navigation. So the second part I would say, so probably in the mobility, how can we get the Husky to really going through that pile but not just stuck on them? That's probably a thing we were looking on, or maybe solved by other platforms. We don't know. And why we put in our Husky that is we have, so they are robots for the course and also robot for the research. So there's a fun fact about our robots is they have like 40 ports of Ethernet. So you can see how there's amount of sensors there, and so there are LiDARs, there are RGBD, there are also millimeter wave, there are also microphone arrays. There are lots of things, but those things are just, we want to try them. So how they could work in such environment, and what kind of interesting research, what kind of creative things we can do on them. So that's a reason why our Husky develop and eventually grows like that. Yeah.
Okay, thank you.
No problem. Thank you.
And now, a presentation from Scinet.ai.
Hi, we are Team Scinet.ai, and we are honored to be part of this competition. Our team is made of myself, the team leader, Chris Fotake, as well as Sapas Das and Shakti Sharma. We all share a mix of skills centered around software development and robotics engineering. One of the main tasks of our robot was localization and mapping. We decided to use the Google Cartographer package, and while it wasn't easy to set it up to work as 3D SLAM, eventually it generated very good trajectories and pretty accurate positioning inside the urban environment. Another advantage is that Cartographer will produce accurate 3D occupancy maps of the environment that can be later analyzed in debriefing. For object detection, we started with our custom YOLO implementation in PyTorch, but that was very slow in CloudSim. So in the last few days, we had to switch to a pure OpenCV algorithm, which while it wasn't as accurate as the neural network, it still produced pretty accurate results. All the detected objects are stored in a queue, and they are periodically sent back to the base station until we get acknowledgement of the receipt. For motion planning, we extracted a simple flat laser scan from the Cartographer point cloud and used a simple PD controller to always explore the farthest sections of the map. We used a saved trajectory to reach unexplored sections of the environment and also to return to base. For the urban circuit, we built on everything we learned in the tunnel circuit, and we had to make significant improvements to our program. And some of the main challenges we faced are the following. First of all, we had to figure out the correct Docker submission format, since it didn't run at all in the tunnel circuit. Then we had to change from our graph map representation to a full 3D SLAM using cartographer, and figure out more efficient exploration strategies. Finally, we had to use OpenCV instead of our YOLO neural network for fast object detection. We are looking forward to the cave circuit and to see what further improvements we can make to our software.
Please welcome to the stage, Marble.
Well, good morning, everybody. So first of all, I'm Sean Humbert, I'm lead for Team Marble. First, I want to thank Tim for the vision to pull this together, as well as the DARPA staff and the SatStop staff. So I think we all should give them a big hand. Yeah, it was quite impressive to see the amount of technology that actually went into the SatStop facility to actually produce all of this stuff. So again, very impressive. Okay, so we're University of Colorado Boulder and Denver campus, as well as Scientific Systems Incorporated, which is a small company out of Boston. So this is roughly how we're distributed across the technology areas. Again, our team is mostly undergraduate, graduate, and postdocs from the institutions that we look at. So this is basically a quick summary of our technology map. The black is what we ran with in tunnel, and the green are the deltas that we added for urban and eventually cave here. So for the perception part of this, of course, we had to add all of the additional modalities to incorporate the new artifacts. We actually invested time in making a pan-tilt mechanism to reduce the number of lights on the platform so that we could have sort of a better view and improved artifact detection. And we also moved from the April tag to the Leica gate, or sort of gate detection stuff. On the networking, tunnel was an interesting experience for us. We had all of this stuff prepared, but our deployment mechanism wasn't working very well. So we've added the deployable beacons and spent a lot of time sort of developing those. And we were pleased with the amount of network connectivity that we had this time around. Our autonomy piece reflects sort of two of our main driving sort of principles, and that's the fact that we assume that the robots are not going to be connected to the network most of the time, so the autonomous piece has to be very strong. And when they are, we want to be able to take advantage of the information. And so we added the collaborative mapping and planning piece, so all of our robots share maps, and we plan on sort of fused or shared maps as well. Our hardware didn't necessarily give us a lot of benefit in that case, and I'll talk about some of that stuff in a minute. And then for the mobility, we ran Huskies in the first one. For that particular coal mine, it's flat and gridded, and that was an ideal surrogate platform to test a lot of the other parts of the program. But we added two different sizes of track platforms as shown on the screen there. We also have been working a lot on the aerial platform parts to cover the 3D stuff. Okay, so as far as lessons learned, I think it was really enlightening to see the differences from tunnel to cave in terms of the environment, the 3D structure, the locations of where all the artifacts were hidden on top of things, on passageways and all sorts of stuff. So being able to negotiate and sort of explore on that 3D level is of course really important. Now, for us as a team, after tunnel, we decided on a more holistic approach for urban and cave. So we sat down and decided what technologies at the end of the year we wanted to have validated and working well going into the final year of the competition. So as you saw on this slide here, there's a lot of green on that chart, right? So in 6 months is not a lot of time to take any one of those necessarily and add it. And so we, and I put a lot of pressure on our team and our students to investigate all of this stuff. So again, I think we had a slightly more holistic point of view, which means that not everything on that chart was absolutely ready for prime time deployment. But also in our case, I think it was difficult finding good places to deploy. We got some great sort of help from various warehouses in Denver, and sort of the first responder community within Boulder were able to give us some opportunities to go do test deployments and so forth. But I think the data we collected this round is really going to help improve and get us to the position where we want to be in Cave. So again, that was a slightly more holistic thing. Now, also I think it's not really a lesson learned, it's a lesson reinforced. But all of our students, so our undergraduates, our graduate students, and our postdocs, this is the most impressive team I've ever worked with, and we would be nowhere without all the dedication and the effort that they put into this project. And so I can't be thankful enough for all of that. So I want to give them a quick hand too. And with that, I'd be happy to answer any questions if anyone has anything.
Hey, Sean.
Hey, how you doing, Mike?
So first of all, just thanks for Team Marble's great collaborative spirit and great competition with all this, with your work. I'm curious in particular about the pan-tilt unit. I think this is something that several of us have talked about probably within this. I'm wondering if you're willing to talk more about the performance of that and what you saw during this competition. You know, things I would be concerned about are, you know, are you able to pan and tilt and capture enough of the environment as you're rolling? Are you moving too fast? You know, as you know, overall, do you just consider that a win?
Yeah, so we ironed out a lot of this stuff through some of our deployments, but motion blur is definitely an issue, right? So I think we had 2 different iterations and 2 different motions you probably saw. One was sort of a discrete motion where it would sit and stop for a little bit. Again, there were still some motion blur issues with that. We also had a continuously panning one too, right? I think we were satisfied with the overall performance. We didn't have a lot of extra time to really kind of sort of optimize our artifact pipeline. And so we did leave a lot of points on the table in terms of being able to detect artifacts. I think we're going to go back and take a look at the data and make sure and try to understand what the benefits and the drawbacks were. But I think overall it was a huge positive. If you remember our Huskies from last time, they had lights all over the place, and it was sort of a disco Huxley, if you will. But yeah, so just having that one LED being able to point in the different environment, I think that really simplified some things. So thanks, Mike. Cool. How are we doing, Nick? Good.
Sean. I was actually wondering if you could speak to, you said you were using millimeter wave radar.
Yep.
And just if you had any sort of wins with that or any sort of takeaway messages.
Yeah, thanks. So that's one of the technologies we're trying to develop is sort of, you know, I think most teams are doing like a LiDAR inertial based SLAM and localization approach, especially for the smaller, like lighter weight aircraft like the UAVs. So we're working on like a radar inertial type localization. And I think we've made some great progress on that. We decided not to field that on the aerial vehicles at this time because we had the Ouster working, we had the slightly larger aerial vehicle. We envision a smaller aerial vehicle in the future where we can use that. We're also, of course, the radar is not as dense point-wise compared to the LiDARs. So we have had some really nice progress for mapping as well. The fields of view are a little bit more limited, but I expect definitely to be fielding vehicles with millimeter wave radar, both doing the localization part as well as the mapping. And again, you guys have seen these radar boards. They're really small, a couple $100 a piece versus the $8,000 for the LiDARs that we're using, right? So. Again, in our project, that's been more of a technology piece that we're pushing on the research side, but we're really eager to get that working. Cool. Yes, go ahead.
Hi, I was wondering if you could speak a little bit more about your shared mapping.
Sure. Yeah, so each vehicle builds its own map, an Octomap, and then when, so vehicles have point-to-point communication, right? So we share that, and then we basically just append that map to the others, right? And so we're looking at best ways to kind of do that. One of our major issues was that, now again, I do take solace in this, like in the multiverse, there's probably at least one universe where none of our real senses dropped out on any of our runs and all this other stuff, right? But So on our RealSense bus, we also had our IMU on that one particular vehicle. So the RealSense went out, just knocked the whole bus out, and then the map that was getting added from that vehicle to our larger sort of global map between each of the platforms was getting frontiers pasted everywhere, like all out of the place, right? So we weren't able to handle some of those technical issues this time, but that's basically it. And I think going forward with this, we did have some algorithmic aspects where we'd weight our own map versus another map from a different vehicle. But when it's bad data getting added in, we need to kind of take out some of those outliers too. So again, I want to be, when we're at Cave, I want to be deploying this, and I think this is such a critical piece going forward in terms of optimization and exploration for the final event. I wanted to get it into this one, and I wanted to test it out, right? Even though we had quite a few technical issues, and the hardware didn't work with us very well, but cool. Good. Thanks so much. All right, thank you all for your attention. And again, it was wonderful to compete with you guys again. Such a great group and talented group of folks, and we're very proud to be here too. So thanks so much, guys.
And now a presentation from Sodium-24 Robotics.
My name is Malcolm Stagg, and this is Team Sodium-24 Robotics. I'm a one-man team. I live in Dallas, Texas. I originally formed the team Sodium-24 to participate in the DARPA Spectrum Collaboration Challenge, which just concluded in October of last year. The name Sodium-24 started off as an acronym for Self-Optimizing Distributed Intelligence Universal Mesh. I've worked with robotics, AI, machine learning, and computer vision some in the past, but the virtual tunnel circuit was my first experience using ROS and Gazebo. I really enjoy working in this field, and I'm very glad to be able to participate in this challenge. My basic technical approach has been to identify frontier points for exploration, sharing these between robots as potential destinations to explore, while attempting to keep the robots fairly distant from each other. The robots return periodically to the entrance for artifact reporting and communication purposes. As they communicate, each robot shares its known mapping information, location, and any known artifact locations. I am now using convolutional neural networks both for visually detecting artifacts as well as now hazards such as stairs or a ledge. Artifact locations are localized iteratively from multiple observations using triangulation. I'm currently exclusively using UGV robots. I was hoping to use one or more of the X4 UAVs, but ran into some last-minute stability problems, so just decided to stick with the UGVs. So I'm once again using the X2 UGV in the configuration with the 3D LiDAR and the HD camera. Each of these robots was 250 points, so there are 4 robots on the team. Time constraints were again a challenge for the urban circuit. There was a lot to accomplish in a short time to deal with the new challenges found in an urban environment. Hazards such as stairs and ledges are not easily detected by LiDAR alone, so I ended up training a convolutional neural network to attempt to detect these hazards whenever the LiDAR detects uneven ground. Navigating downstairs was avoided due to the limitations of the X2 robot, and though the robots had very limited success in dealing with railway tracks, once they are on the tracks, they are often able to navigate fairly smoothly along by detecting the slope angle of potential obstacles. To handle communication challenges in an underground environment, I'm using each robot as a relay node containing a cache of peer. There were some significant improvements made to the system in the time since the tunnel circuit. Several bugs were fixed, such as one coordinate mix-up causing inaccuracies in the artifact localization, the handling of steep slopes and drop-offs, and the sharing of frontier points was also improved. There are still a lot of improvements to be made, though, including reducing the large number of false positive detections in both artifact and hazard identification, better handling of stairs and railway tracks, and finishing work on the UAV control. During some final testing, I also noticed an issue that robots can sometimes become stuck due to problems with merging the maps shared by other robots. And unfortunately, this couldn't be fixed in time. My number one lesson learned is that it is very important to test the system early. Waiting to do a lot of testing until the last minute was a bad idea, since the online simulator had issues when the user demand was very high. Also, some problems, such as with the map merging, only revealed themselves during the full-scale system testing. So it would have helped to do more of this earlier. I found it very interesting how urban environments, which we often take for granted, pose some serious challenges for robot perception and navigation. Stairs, ledges, and especially railway tracks were surprisingly difficult to handle or avoid. The robots had very limited success in dealing with the railway tracks, especially while trying to enter or exit the tracks. It was very easy for a robot to get its wheel stuck in a groove or caught on some obstacle. Once again, I really enjoyed working on the urban circuit, and I'm looking forward to seeing what new challenges come up in the cave circuit. Thank you for watching, and thanks to the DARPA team once again for their great work in putting together the urban circuit.
Please welcome, from the systems competition, Coordinated Robotics.
Good morning, everyone. I'm Kevin Knadler from Coordinated Robotics, and I'll be telling you some about our systems track entry. Okay. So we're a group of roboticists from Coordinated Robotics, which is myself, and we also have the California State University Channel Islands group, which did most of the work for our systems track, and we also have a group of students from Sequoia Middle School who helped assemble some of our smaller robots. So we had a large group of people. You can see from our picture there that we have a lot of people that worked on this. At California State University Channel Islands, they have a new mechatronics program. It's in its second year. So all of the students are freshmen and sophomores that are working on the project there. They're led by Professor Isaacs, who's helped coordinate and make this a successful project. Since they're freshmen and sophomore, I wanted to remind everyone in 2 years to recruit them to your school to be graduate students or hire them. Let's see. So back on the other slide, though, our goals for the urban circuit were to score more points than we did in the tunnel circuit. And so since we had scored 0 points at the tunnel circuit, that meant our goal here was to score 1 point. And so we were very happy. We came here. We scored that point. Each of our ground robots that were primarily, again, built by the students and at CSUCI were able to deploy on all 4 of our missions. So all 4 of the robots deployed on all 4 missions, and so we were very happy with that. They started their work in November, so all of those robots were built between November and now. And so that was, I'd consider a great success to their dedication and work. Let's see. Our technology approach, we came in with a team of quad rotors and ground vehicles, intending to use the quad rotors for the vertical sections and the ground vehicles to act as, or actually all the vehicles could act as communication nodes, but for the ground vehicles to explore and then the UAVs to deploy when we saw a vertical section we couldn't get to. We didn't actually have time to get the UAVs working any better than they were at the tunnel circuit, so we did not deploy them. But what we were able to do is we focused on getting all those pieces together for sensing and system integration. We were able to use Lego Loom for localization using the Velodyne LiDARs. And so that really helped us to get to the point where the robots knew where they were. We had sonar if we were to encounter any fog that did not allow the LiDAR to see. Then for object recognition, we used primarily vision-based processed with TensorFlow. For the objects we did see, we actually reported one of them correctly, and our chain fell through there. Went through the whole process to get back to there, so that was a success there. The undergraduates did a lot of work labeling images. I'm sure all of you know about the fun of labeling images, so that was one of the projects they spent quite a lot of time on in addition to building the robots. Let's see. So on autonomy, one of the key things that we'd like to get to, but we're not at yet, is to get the robots being autonomous. And so we have a team, we brought a team of 10 robots, and we're doing teleoperation. And so that means at most, any one of those, we have at most one robot running at a time right now. And that is a very inefficient utilization of those resources. It turns out to be even less than that because sometimes robots get stuck and need to switch over. Sometimes we need to deploy a new robot. And so all those things add up to we were probably at least one robot was moving probably 60% of the time, which is not very efficient. And so going forward, we're really going to work on that autonomy. We did not use the existing autonomy because we hadn't tested it enough. And so you really have to test the autonomy to get to the point where you trust it and where it can react in a controlled manner to situations it doesn't expect. So if it gets to a corner or gets stuck, rather than just continuing, it needs to be able to indicate that it needs human supervisory help. We do plan to continue to take advantage of that human supervisor to help get the robots unstuck, because even with the limited perception the humans have through the view, they can really help get robots unstuck when the autonomy gets into a situation it doesn't understand. Okay, lessons learned. So we queried the whole team for their lessons learned, so we have an interesting list of lessons learned. One of the fun lessons learned, one of the students said that they thought this would be a really hard challenge. And so their lesson learned is that it was a really, really, really hard challenge. Another lesson we learned is having a variety of platforms is important. We primarily used our two types of ground vehicles. What ended up happening is getting the larger ground vehicles through some of the narrower doorways was hard or even impossible in some cases. And so we had some smaller ground vehicles that we were able to use. And so having that variety of platforms allowed us to get in and check out things that were not possible. And so our point breakdown ended up being roughly half and half between the large and small ones. And so we thought that was really good that we were able to do that. Now, let's see. Another lesson learned was be willing to make adjustments. We weren't as prepared as we'd like to be coming into this. And so as we went along, we made adjustments. We changed our mapping approach in the middle. And so that was an adjustment that really helped us. We changed what sensors we had on various platforms. We moved sensors around, added sensors. And so all of those adjustments and changes were important to us in this case. We would like to be at the point where we're fully tested before we get here, but we'll hope for that, but I don't see it happening right away. Another thing, all of the teams here are very supportive. And so we've been trying to encourage myself and the whole team to go out and talk to those other teams. Because it is really important when you talk to those teams, you learn, and you can share information with them. And that collaboration is really helpful, and it's been particularly helpful to us. So thank you to all the other teams for talking to us. Another lesson learned. We knew this coming in, but we really learned it here again. Limited communications is a really big factor. For teleoperations, basically, if we lose communications, the robot is stuck. We had an idea when we were going to lose communications, so we never actually got a robot stuck, but it limited how far we could explore. And so that limited communications is an important lesson learned. I said this last time, testing is key. We didn't test enough. We probably won't test enough next time either. But the more you test, the more successful you can be. That testing is hard and expensive and takes planning, but that is what is key. Getting those robots tested, finding the corner cases, fixing the issues you find from that testing. Next lesson learned. The undergraduate said this was a great experience for them. Professor Isaacs and me also had a great experience, but if you have space on your team, bring some undergraduates along. I think it's been a great experience for them in terms of the learning and the future roboticists that they will become. Lesson learned for me. Last time I came as an individual. That was interesting, but I wouldn't call it fun necessarily. This time, the team has been really supportive, and being part of that team has been a great experience. So all of you that have a team, appreciate them. Let's see. Okay, so just a thank you. Like I said, all the teams have been very supportive. A special thanks out to Team Explorer. They loaned us an Arduino that we used on one of our robots, and so we appreciate that. But all the teams have been very supportive, and it's been great working with you. And again, thank you for the staff. This has been a very well-run event. Rules are clear. The staff is helpful. They make sure that we're doing what we're supposed to. We appreciate that. So that was all I had to say. Does anyone have any questions?
Hey, Kevin, thank you. If I'm remembering the scoreboard from virtual, you did really well there. I'm curious about, and if I'm remembering correctly about what you said you're still not able to get the autonomy for the systems challenge. But I'm wondering whether you can make some conjecture on if you had time and the opportunity to do that, would you be essentially trying to bring that same code over, or what were some of the things that you saw from the systems challenge that might have changed your strategy kind of more fundamentally from what you did in the virtual?
Yeah, so right now they are completely separate code bases. There's not really the learning that we want to go on. So one of our goals over the next 6 months is to be able to run our robots in simulation and to be able to share code from the simulation into the systems track. It was just a time constraint right now, but that is where we want to get to. And I'll come back to one thing. I forgot to mention one important lesson learned. Naming the robots is important. I thought it was just fun at first, but when you can refer to the robots by name, it makes them easier to remember, and they have sort of personalities. All robots have a little bit of personality, and so being able to name them is an important thing. Okay. If there's no further questions, thank you very much for your time.
We will now break for lunch. The program will resume at 1:15. Please take your seats. The program will resume in 5 minutes. Please take your seats. The program will resume momentarily. Please welcome back SubT Challenge Program Manager, Dr. Timothy Chung.
Great, welcome back everybody. I hope everybody had a good lunch here in Olympia and had a chance perhaps to interact with your fellow SubT community members here to exchange ideas. To that end, I'm pleased to get back into the technical interchange meeting. And first up, we have a presentation from one of our virtual teams, the Flying Fitches.
We are the team Flying Fitches from Sophisticated Engineering. We are a small team with 4 team members. Our team is located in Germany, in the area around Frankfurt. The team consists of 4 team members with different knowledge and experience. On the one side, we have 2 team members with many years of experience in programming and solving problems, an aerospace and aeronautics engineer, and a mathematician. On the other side, we have 2 young team members who bring in creative new ideas and totally different approaches to solve problems, a physics student and a mechatronics student. We do not work in the robotics area and are still newbies to the technology of robotics. So we are only spare-time robotics programmers. To explain our technology approach, We will describe our approach, how we do the difficult debugging and testing in the distributed environment of the robotics simulator. We will speak about our model for building up a map. We will give some information about the needed redesign of our software architecture. We will describe our own built messaging system, and we will explain the usage of a team base and our robot team structure. Debugging in a distributed environment is very difficult, especially if the error appears randomly after approximately 10 minutes. Usually, we didn't have a clue what is going on and had to repeat the test runs a few times in order to identify the problems. To avoid these time-consuming reruns, we built up a system to save the situations during a test run. In the next step, use this data to retest and debug the problematic situations to solve the errors. In the tunnel circuit, we used a simple system to generate a map. It consists of nodes and edges. Nodes represent crossings and have a position. We realized that this model is too simple for the urban circuit. With a simple model, we cannot cope with a hall or a bigger place. So we enhanced our model, but we did not have the time to complete the implementation of the enhanced map model. As an outcome of the tunnel circuit runs, we recognized that we needed to redesign our software architecture. Synchronous service calls were causing time gaps of up to a half second. So we needed to replace them with asynchronous topics. We also needed to split off a function with a time-consuming algorithm in a separate ROS node. As a result, now the robot is not left alone for more than 0.1 second. We implemented a small messaging system for the communication between the robots. One of the main assumptions is nobody is lying. But guess what? Our robots were lying. This was due to a software error, and our message system ensured that this wrong information was spread to all the other robots. We use a team base to coordinate the communication between the robots and the team base. The team base is not moving, it is placed on the staging area and stays there all the time. For this functionality, we designed a new robot to reduce the costs. Unfortunately, the pull request for the team base was not approved because too many pull requests for other new robots were raised. So we had to use the X3 copter again as our team. For our robot team, we used an X3 config 1 robot as a team base, and we used 3 X2 robots with 3D leader and a front point leader. We learned some lessons in the urban circuit. Reproducible tests are essential. We would say software error fixing is not possible without them. The architecture of the programmed ROS nodes is very important. If the architecture is bad, one will not be able to fulfill the requirements in such an environment. The missing detailed knowledge about the simulation software is still a big drawback for us. The biggest problem is still the exact enough position localization. And finally, we need more time.
Please welcome to the stage, Cerberus.
Thank you, everyone. First of all, let me thank all the people from DARPA that contributed to design this competition. For us, it's amazing. It's also amazing how hard it is, but that's the beauty of it. Let me also congratulate all teams, and especially, of course, the winners, the best three, CoStar, Explorer, and CTU Crash. Amazing job. Having said that, let me continue with my presentation. So we are Team Cerberus. We consist of a set of organizations. It is us from University of Nevada, Reno. We have two groups from ETH Zurich, ASL and RSL. Then we have University of California, Berkeley, Sierra Nevada Corporation, Flyability, and as of the last 1 year and more, Oxford Robotics Institute is an integral part of the team. Now, I guess you understand that they are very good. Some of these people, all of us, but I want to refer to everyone other than me. These people are very talented, but we are also in two sides of the Atlantic, which means that there is some challenge in the integration. And also, we bring a very diverse set of systems. And the most important thing we want to mention from the beginning is that our approach is to start from the beginning with one unified solution of robotic systems walking and flying, with a hope and belief and confidence that, in principle, this type of systems can resolve the challenge of subterranean environments regardless of which circuit we are participating now. Of course, there is a lot of effort to make this happen. So this is what we brought in the tunnel, in the urban, excuse me. We brought two animal bee robotic systems. This is the current ongoing robotic configuration of Animal that people might be familiar from videos and so on and so forth. We brought three traditional quadrocopter platforms. We call them Alpha, Bravo, Charlie, and two collision-tolerant flying robotic systems, which we call Gagarin. And then these are our main robotic systems for exploration and scoring artifacts and doing the mission and so on and so forth. And we had two systems that were somehow supportive, and I will consider them trails of our past in a way, that contribute into the reliability of the overall team. But again, in principle, we would like to focus purely on the walking and flying systems in the future. And actually, already in the urban, all our points but one and most of the exploration did not happen with any of the traditional systems, happened with walking and flying. So this is what we brought. I want to highlight two things for the technology for everybody to understand, and then afterwards I will say the lessons learned. So the walking and flying systems, of course, they are largely different between them. But after the platform level, the mapping side is now unified among the systems, both at the level of each individual agent, which fuses LiDAR, cameras, IMU, and so on and so forth, but also at the level of combining the maps among the robotic teams. Currently, the combination is based on vision. Then the path planning of each individual robot is also now unified with extensions, of course, between ground and flying to account for traversability for animal versus different types of challenges for flying robotic systems. A key part, however, is that we try to unify software to the extent possible, not only among our teams, but also among our platforms. So with confidence, and with many lessons learned from the previous circuit, I would like to mention what we learned from before that we improved significantly now, and I hope DARPA people saw that in the competition, what we learned in the urban and what this means for us for the cave. So first of all, system reliability is something we improved a lot from the tunnel circuit all the way now. Every system was reliable from the beginning. It operated, it functioned, it continually on its own, explored, and one day in the second alpha, that we thought one of our systems was not working, actually was exploring on its own for quite a while. But yeah, it should return in a different place. But that's an error in the state machine there. So system reliability was something we learned from tunnel, and we improved a lot all the way. Advanced autonomy was another aspect. And of course, multi-level exploration was something that was not there at tunnel, and we knew we had to develop for the urban, and we emphasized on staircase, ascent and descent, both with walking and with flying. So we're also happy to demonstrate that also with flying robots. Now, lessons from urban. The first one is more integration and more field testing. I think everybody can mention this, but I think especially for us being on two sides of the Atlantic, this is a lot of effort we do to make sure that these systems are integrated. So we fly back and forth to achieve this. We reach a certain level at the moment, and things work pretty reliably. We had some glitches, and I will mention one very open that I'm sure everybody from DARPA will have thought. Animal did not have the camera facing up. So even if there was an event, we didn't see it. So there are some limitations on integration, but in principle, things were very well integrated among each other. The second thing we learned from urban is that tethers were OK for the tunnel circuit in order to extend communications, but they were much more hurdle for the urban circuit. And again, as mentioned, this is a temporary part of the process of building the Cerberus robotic system. Communications remains a big challenge for us, less for this one, to be honest, but I think in general it should be something that is of particular concern. Autonomy is something that we learn again how much improvement and how difficult it is to achieve on a complex robotic system of systems. For little things, such as what I mentioned, that one of animals explored on its own, we're walking around, and we only saw that this happened after we finished the mission just because we had a small error in the state machine. To big issues, for example, that we were continuously exploring with our robots, but there is one thing to explore the underground environment in terms of unveiling new volume, and there is another thing to have a behavior that leads you to artifacts. So in general, we had to intervene sometimes with manual recommanding of the robot when it was reasonable for the human supervisor and correctly expected that some areas likely have artifacts. The automatic planner was guiding the robot in a different direction because it was much more likely to explore new space. So we will now proceed not only to explore, but also build the behaviors required in order to search for entities of interest, which for the DARPA SubTv are the artifacts that are described, but in a broader concept of things, this should also enable missions that are of interest to DARPA. And then, of course, bigger challenges that relate to how robots collaborate among each other, which at the moment heavily rely on the human supervisor making some basic reasoning about where each robot does. But these are things to be explored in the future, and these are also things that we already develop as we go all the way for the cave circuit. Other things that are important is, we didn't face it, I believe, in this competition, maybe because that's until where our robots went, but I'm pretty sure the perception degraded aspect is something that we have to continue for the future. And the last thing for autonomy, we can do all the amazing work to go down the difficult part, like going down the stairs, and we can still do a mistake on the landing pad of the stairs. So this is also some things that relate mostly to experience and to integration that, of course, we have to improve a lot as we go. But these were the main lessons learned from our side. And again, of course, we are on track to try to resolve this for the cave. So what we will bring in the cave on the basis of the lessons learned and on the basis of decisions we had made as a team from beforehand. The first one is we change the robot. We will bring the new animal robotic system, and this is on its way for being integrated for the challenge. It's larger, newer, and much more powerful with respect to the motors. So this is also something that will be very useful for the anomalous terrain that I'm pretty sure Victor is preparing for the cave. The second one is to co-deploy the flying from the ground, which is something that we had planned, but we didn't have time to finish, and therefore we only used flying robots to explore a set of alpha and also to go down the stairs again at alpha. Resolve and improve comms, which for us I think it's something that is a very important issue that we have to improve from our side. As mentioned, embedding the behavior of searching for artifacts versus merely exploring, which our robots do already well, but they have to search to find the artifacts and score on their own without the need of any human input for that matter, or without the need to exhaustively search in order to find the artifacts, but kind of a reason about where objects of interest might be. And we are even more committed, and we have a nice plan for enhanced integration among our teams. One of them is that we exchange people among our two sides of the pond, which is also facilitates integration much better. So this is more or less our plan. These are the lessons learned. I want to emphasize again from my side that we are grateful for the experience we had here at the competition. Congratulate again those that went better than us, and promise, of course, and with confidence that what you see with walking and flying robots will keep improving as we proceed in the next phases of the competition. Thank you.
Hey, Costas. Just was really interested in your multi-robot mapping that you were talking about. Could you just explain, are you sharing information between robots as well as back to the base station? And did you find that gave you a lot of advantage over when you weren't doing that?
Yeah, so at the moment, first of all, in this competition, largely because I believe the environment was highly structured, it didn't appear to be much of a need. So as we were integrating and we were deploying in the competition from the first stage, we saw that the default map of every robot was sufficient. But what we have as a functionality is that each robot shares a very compressed part of information to the ground station, and then on the ground station, we co-optimize the maps among the robots. But it pays off when we go significantly deeper, when robots have seen the same areas, of course, and open sharing information. We have one flying robot that does not have the computational capability to run this. So there is one type of the systems that do not run this particular software. But we believe that if you think of in the broader context of things, not how we do only in one circuit, this is something that is of very high importance when you increase the size of the fleet and when you go deeper and you cover more common spaces among our robots. And of course, when some of the environments are not so well structured as the urban circuit was. Because for LiDAR, this environment was pretty good. Thank you. Thank you.
And now, a presentation from Kolembala.
Hello, everybody. We are the team representing SSCI, and we are excited to share with you a little bit about our Urban Circuit Challenge experience. Our Subterranean Challenge project is entitled Kolembala, Communication Optimized, Low Latency Exploration, Map Building, and Object Localization Autonomy. Let me introduce you to our team. Our team is composed of 4 members, with 2 senior and 2 junior members. Hector Escobar is our principal investigator, Neil Johnson is our senior research engineer, and Derek Vasquez and Brett Fotheringham are both engineering interns. When we started working on the Urban Circuit Challenge, we had 3 key expectations. First, to demonstrate that our simplified, bio-inspired approaches could serve as robust solutions to a number of complex problems. Second, that our system could be adapted to a variety of different vehicles with different sensor configurations with minimal integration effort. And lastly, that we could piece together a fully functional system using algorithms we had developed for separate projects to make our agents capable of dealing with the complex environments of the urban circuit. Our approach to the urban circuit consisted of a suite of bio-inspired algorithms used for rapid navigation, mapping, and search of an unknown environment. Our goal was to implement these algorithms using low swap sensors, all while requiring low levels of computational power. A key component of our approach was to detect environment changes and classify them in categories such as corridors, dead ends, open spaces, etc. While this problem is challenging with low-grade sensors, it allowed for the agent to adapt its algorithms and priorities accordingly, allowing for more intelligent behaviors. Our robotic team consists of 3 vehicles, 2 CoStar Husky robots with 100-meter 3D LiDARs, and 1 X1, also equipped with a 100-meter 3D LiDAR. We plan to use the SSCI X4 vehicle configuration for our next circuit submission, but we're not able to use the vehicle configuration for our urban circuit submission because of time constraints. The final component of our approach was to organize our control system into control primitives such as wall following, tunnel centering, room exploration, etc. This modularity allows for quicker development of and flexibility for upper-level planning and tasks. To conclude, we'd like to mention some of our biggest surprises and include a few final comments. The biggest surprise for us was the quick turnaround time between urban circuit and tunnel circuit. This quickly showed us which parts of our system were generalized and robust and which parts were not. The second surprise was the increased difficulty agents had in returning home after exploring for an extended amount of time. To deal with this tendency to get lost, our agents were only allowed so much exploration time before they had to return to the base station and report their artifacts. Our final surprise was the difficulty our agents had in getting to and from the subway rail sections of the environments. Prior to this point, our agents were able to deal with obstacles in terrain using a very general navigation system, but this obstacle required special treatment and development time. Finally, our current system was fun to develop and improves upon our SLAM algorithm, avoids drop-offs, and has many other works in progress that we will continue to develop for the following circuit events. We hope to decrease our reliance on 3D LiDAR devices and transition towards lighter weight, lower cost sensors. Secondly, the environments are challenging but enjoyable to work on. Long passageways, like the subway tunnels, still lead to substantial SLAM drift that we are attempting to address by combining visual and laser-based SLAM methods. Thirdly, we committed a lot of effort to submit new vehicle models, but more work needs to be done to effectively use these new vehicle configurations. We plan to submit vehicle configuration updates to address sensor placement issues. Track vehicles are needed to approach diverse environments and obstacles. We hope that many system teams will be able to submit their models to the tech repo before Cave Circuit to further enhance the possibilities. And lastly, we are transitioning more and more of the work to younger staff and interns. This is proving to be a very effective proving ground, an opportunity for students and young engineers to contribute to our team at SSCI. We hope you've enjoyed this look into our work for the Subterranean Challenge and are excited to continue working in preparation for the upcoming Cave Circuit Challenge.
Please welcome to the stage, Cyro Data 61.
Do I just press the green? Yeah. Good morning or afternoon, everyone. I'd just like to start by saying how proud I am to represent this team, and I think secondly, like how much fun we've all had being here. We really enjoyed this event, both how it's set up and hanging out with the other teams, even if some of them beat us at bowling, which is rather upsetting. Anyway, we're a team based in Brisbane, Australia, and Georgia Tech is also part of our team, in Georgia, obviously in the US. Emerson is a drone autonomy startup in the same site as us, just outside Brisbane. And they've obviously brought those drones that you've probably seen around the labs. And they have a hover map, basically mapping autonomy solution hung off the bottom of those. And that's actually a commercial product. Any one of you can go buy that, use that mapping solution on any robot. And then Cyro, we're the prime for the team, have been focusing on the ground robots and the SLAM solution. So essentially, how do we, I think one of the really cool approaches of our team has been every single robot has exactly the same mapping solution on it. And I really wanted to deep dive on that a little bit today. But sort of as an overview, both the drones and the ground robots have these packs. Again, the one on the drone is called Hover Map. It's actually a commercial device. The one for the ground robots is a lot more experimental. It's beginning to look pretty polished, though. We've had, deal with 40-degree centigrade temperature swings in coming here. So there's a lot of bits and pieces that sort of broke in either, 45 degrees Celsius weather or 0 Celsius weather over the last year. And so it's getting pretty shaken out. But again, all these robots are building these maps and sharing it with each other. They're detecting objects, with deep learning. And I think one of the new additions for this is semantic maps. We're adding in stairs and doors and really trying to populate those as sort of features or tie them to our map. And so I kind of wanted to focus on that aspect of what we're doing today. We had quite a few questions about it. I guess first, what's new from Tunnel? There's a screen there, perfect. We didn't bring Bruce, our hexapod. It's getting a lot better, but it's still, I think, one of the big lessons learned was how robust these systems have to be, right? If you spend 3 minutes with a platform on the starting line, that's a big percentage of the time. The other thing is we're launching the drones off the back of the Titans, which was a big, fortunate decision. We practiced that because, that got us through some doorways, really sped up things. And then we actually moved to Radiant radios. So we had been building our own communication system, and we weren't making enough progress. We talked to UPenn, and we just sort of bought a set of these, and that really allowed us to focus on the autonomy as opposed to developing sort of this pretty critical part of hardware. So that is a big change. One thing I think, we're pretty proud of, I'm very proud of the engineering team that has been putting this stuff together, right? So as I said, we have cameras going over MIPI buses to an Xavier. Those things don't really fault. We don't have things falling off buses anymore. And this is kind of, if you want to talk about how to do this, if you guys are interested in having a lot of cameras pumping data, you can talk to Dennis in the back. He's spent a lot of time getting that to come up reliably. Maybe he has some tips if you want to try it. But I'd say that we didn't think about stuff falling off buses or any issues like that this time, which felt really good. So I think the coolest thing, and I think the most exciting thing that a lot of teams are doing, is really this multi-agent autonomy, right? And so what you see in this map is one of our first runs, and you see the red dots are different robots, and the pink dots are frontiers. So where should robots go? And these robots are sharing that information amongst each other. and basically saying, I'm going to go here, a robot A should go here, robot B should go there. And that's a shared map on every single robot. So every robot is computing a global map solution from everybody else's frames. And then on top of that, we can share detailed information like, this is the transition from a known map space to unknown map space. Drones can either, go up in the air or go down holes that other robots can't, which we actually accomplished on this, which was a great moment. But this is, it had some faults too, right? We didn't explore enough small rooms. We prioritized larger spaces where there were fewer objects. And I think that was probably the biggest fault we had with this setup. And I think like most teams, right, we'd practice in, a couple of different, we've practiced in an underground parking garage and a construction site, and somehow, all that testing didn't quite translate because of the scale differences and some assumptions made. I guess there aren't many abandoned nuclear power plants around, so it was a good choice. But I sort of wanted to deep dive in, what our mapping is, because this map sharing ended up being a really critical part of how we do autonomy, how we've decided to go about things. And so what you'll see, we have a spinning LiDAR, right? So we get these very dense point clouds. And ultimately, we can't share that data live, but we do, compress it down into a voxel map. And there's a couple papers on this, but it's offset voxel grids of different resolution, and sort of what you would expect. But that's what I call circles in this talk on the right. So, point clouds become circles, it's a voxel map. But there's a really cool thing, the LiDAR is spinning, everything's sort of vibrating and moving. So we have this continuous integration approach where that's sort of done through continuous integration of the IMU, correcting things in 5-second chunks. And that's a frame. So this corrected 5-second chunk of LiDAR data is called a frame. And these are actually quite low bandwidth to send these around. If you send one of these every 5 seconds, it sort of works out to be like 18 kilobytes a second to push these across all robots. And so that's low enough bandwidth that we can share these frames amongst every system, the ground station, all the robots, very easily. Well, not very easily, through a lot of hard work and when we have good physical comms layers. And then what we do is we basically solve the pose graph problem. So every robot has all these frames from every other robot, and it's just incrementally solving the global SLAM solution on every single platform. And that doesn't imply that each robot has the same global map. They might have partial information. The order of the things coming in might have actually solved differently. Possibly one of them couldn't find a solution. You never know, right? But the point is that this allows robots to communicate pretty deeply about where they've been, who knows what. And telling one robot to go somewhere that another robot's been is really meaningful, right? It can literally say, I've never been there before, but my friend told me exactly how to get there, and we've done that quite a few times on this trip. A really new bit of technology, which is actually inspired from the Pluto's team's paper, is something we call Mule. So this was written in the last sort of 5 months, but you can imagine, agents aren't always in direct communication. In fact, we had many times in this challenge where several agents were off on their own beyond comms and talking to each other. And so, maybe robots have different numbers of frames, right? They obviously have all their own frames, but they may not have the frames of every other robot. And so really what happens is as they come into communication contact, they sort of say, hey, what do you know about? What do I know about? And they keep basically shuttling data back and forth from each other and sort of filling up their manifests, right? And so we call this muling because in the case, the best case we had actually was the drone went in, the drone and a Titan went in by themselves. The drone did this great mission. It downlinked all its data to the Titan robot, which drove back and then gave it to the base station, right? So that happened for us. We did actually have a lot of problems with this system on day 1 and day 2. Again, the sense of scale, I think it was the first time we had all our robots together, was at this event, partly due to, weeks and weeks of shipping lag and stuff like that. But like any time you bring new stuff together, it breaks. And so unfortunately, that was sort of the first 2 days. We really focused on testing this and developing this even further. But I think, I think a really cool aspect to this that was highlighted, so I just say in the tunnel event, we didn't do robot-to-robot sharing. We basically had robots just share back to the base, so we didn't have the muling system. But what's really cool is only one robot in our system shoots the gate or localizes against the gate, right? The first robot says, oh, I see where the gate is, and this is attached to my first frame. And then it shares that frame and that gate with every other robot. And so we actually had this occur in the tunnel event where the drone went far further in than the ground robot, and it detected a person. And what it's actually reporting, right, is that person in the DARPA frame because another robot had seen the DARPA frame. And I just thought that was really cool. So, and it appears to work, which is even better. And I think at the end, so this is an offline process data here, but I think, again, the coolest thing about this is just seeing multiple robots work together. And so what you're actually seeing, if you look in the bottom left, you can see the outline of the Titan robot, right? And what this is all the point clouds. So this is the point clouds on the drone robot. But again, every robot has the same mapping system, the same capability. And you can see it took off from the Titan, which is in the bottom left, and then the Titan drove off somewhere else. And then you see the line where it flew off and it flew down some hole somewhere. And it came back, and you can see the DARPA staff look like ghosts picking up the drone, an hour later. There, right? And this is built up, like as an offline, globally optimized version of what we're doing incrementally online. So, as processing power goes up, this is hopefully what you would start seeing online as a robot. And this is just an intensity colored image of, was it alpha course? Beta, yeah, okay. But I just thought I guess I looked at this, I was like, well, that's pretty cool. That's just LiDAR points, SIL4 globally, right? And then again, I think just to sort of highlight, that collaborative aspect, this is the same thing where the drone went down a hole and came back, landed, got that data back on a different robot back to the base station. And again, just to reiterate, this, we didn't push all these points across. It's not like the base station has an image that looks like this, but this is what each robot has on board. So lessons learned. I think the big one was we'd worked with BA5 with these Titan robots and their police robots, and we'd assumed those are the robots going up and down stairs. So we've driven them up and down stairs a lot. And then I guess Victor probably decided that stairwells was a really good thing to throw at everybody. And we kind of went, that doesn't quite fit. So fortunately, we had these Super Droid robots, right, which are small track platforms. And the thing is that, they're cheap, right? They're 8K. They went down the stairs really well. That was with about a month's worth of, like literally a full-time's month worth of effort, I'm sure. But, we switched off to using those to go up and down with their flipper arms. And it was really just surprising how effective they were. And I think one of the reasons why they were so effective is because you can just pick them up and put them places. And I think coming out of tunnel, we really realized the value for a large, powerful robot that can just blast through things. And I'll try to share some of the videos too of Titans just driving over things in the urban environment because it loved, we went up on these wooden planks and I think we almost hit a backpack on a wall with it. It came back down. But, just that size has its benefits, but the smallness of something that you can put downstairs and test with does as well. And so I think the heterogeneity of that sort of set of systems really became clear in the last month and really became very apparent during this competition. So I think that's the primary lesson learned. I don't know if there are any questions. Sean, just one sec, sorry. So one other thing is Emerson is actually in the back and they are hiring.
Congratulations, Nick. Great job. So you said the drone took off, flew away, and flew down a hole. That was actually one of the coolest things I saw in the competition. Can you walk us through that a little bit? When did you decide to launch the drone at that point? Was it able to detect the shaft? Just kind of walk us through.
Yeah. So I think what happened is the Titan robot basically, we were trying to get it, as I said, into large areas, space areas, right? And it drove, I can't remember, I think it turned, as opposed to the first time, it sort of turned down there in the first left. And then the operator was like, oh, I see a big shaft in the ground, right? And you could see that from the map coming back. And we'd been like, thinking, what's the best use case of a drone, right? Things up high, going through places the ground robots can't go. And so we were kind of like we initially really wanted to run the drones inside the big reactor. We think they would have done really well in there. But shafts was another big one, right? Like, oh, if we find a shaft, let's just do it. And so then the operator was like, right, I'm going to go launch the drone. And so they did. And then what they did is they sort of put a 2D waypoint, which is sort of like a big area bubble, like go over this way, like towards the hole, on top of the hole. And then they put what I guess Glenn calls a 3D planar waypoint, or it's basically like a waypoint lower down underneath the hole that said explore out that way. And so essentially what happened is they sent those commands through, and then the robot basically just took over and then just decided to fly down the hole on its own. With those it was given a set of commands, and that was all it was given. It did its mission. It ran out of battery. I think 7 minutes later, the low battery alarm triggered, and then it said, I have this much time to make it back, so it actually made it all the way back, which there was some sighs of relief, I'm not going to lie, when it made it back. But yeah, that was it. And so it was a bit of operator was definitely looking for something to go through like that, but it wasn't like fine details or anything. It was like somewhere above it, somewhere below it, go for your life kind of thing. Eric.
Thank you for sharing so much information in detail. And I'm quite curious about the frontier part. So you say that robots share the frontier from one to each another.
Yeah.
And so how they decided and coordinated that which robot should discover which frontier? How do they optimize the process?
So I think like most things, we actually have Georgia Tech here. So there's Matt and Shu who are back there who have actually done a lot of the thesis work is based on that. I would be lying if I said we managed to implement all that in time for this competition. So I think really what happened was, it was sort of a combination of things like, so just every time a frontier is created, it gets shared with every other robot. But how they decide to go there, as opposed to what we wanted to have was a more complicated sort of bartering system where they're sort of saying, okay, I know you're going here, you're going there, and to sort of do distributed decision-making like that. And that's what Matt and Shu have been working on, and if you want to talk to them about it, you really should. What we really did was we just, like running out of time, is because we also threw frames and there were every robot's been driving, we just weighted frontiers near where other robots were, sort of we costed it more heavily, and that kind of formed this sort of naturally distributed way where you're not going to go after someone else's frontiers because they're already there or they've already traversed near that area. But of course that also has ramifications, like if someone's been driving out in front of a doorway the whole time, you're not going to want to go over and explore in the room, which was one of the issues, I believe, with what we had happen. So again, we had better intentions, we ran out of time, and we're going to keep working on it. But
so our lab has done a little bit of work with the surfable mapping. Super cool. Is that a derivation of some kind of like Connect Fusion or something like that?
So the original paper was not Rod Zott, but it was called Atlas Slam. Who is the main author? Can you just yell it out? Mike, yeah, Bossy, yeah. And so that was, Mike Bossy was the main author when he was at Cyro doing that. So we can share that with you, but it's basically been a lot of engineering on top of that. There's been some other cool papers along the way, but that's sort of the fundamental paper that's probably the best one to read.
Great, thanks.
Please welcome from the systems competition, Robotica.
So it's me again. I'm sorry to take your time. So Team Robotica, this time the pictures are back from the tunnel circuit, but I will talk about virtual now. I realized that actually in this room there are not many people aware what the virtual is about, because most of you are the system. So I will just briefly review what's going on there. So at the beginning you have 1,000 credits, and you can buy robots. There are 4 types, and yeah, you can see it on the right, falling down from the platform. And so what we did, we really wanted to do it one-to-one, so we bought 5 vehicles. And in order to control them, we create new model, which is Robotica model name, which is RGBD camera plus 2D LiDAR. Okay. So this is briefly, again, the overview of the team. Primarily, we started with Robotica CZ. Again, on that website, you can see history, how we started 1.5 years ago. Cogito team involved at the very beginning. Then later, University of Life Science helped us with the recognition of artifacts. And later, we decided to start the Robotica International as a part. And Robotica CZ is now part of the Robotica International. Actually, these slides were used for the virtual tunnel originally. But they are, I will also talk about the changes since the virtual tunnel. Most of you from Pittsburgh came home and relaxed a bit. For us, it was just the opposite, because we had 1 more month to finish the virtual. But it was different now with the urban circuit, because we had to finish the urban circuit before we came here. And it turned out actually to be better, because we didn't have to worry about this virtual world anymore. And now, it was a nice surprise. We are happy about that. But the solution is more or less the same. It's this also for the system track. So what's the simplest one? Follow the right, left wall. And surprisingly, you can get quite good feedback. So what you can do, if you have not only 2 robots, so not right and left, so with 4 robots, you can send 2 robots far, and 2 just exercise it slowly in the nearby area, because the robots may not return back, as you know. And 5, why not to use 5 if it's available? So the one was backup, similar to case 3 in system track. Fuzzy local planner sounds fancy, but the idea is simple. Suppose you just explore the world, and at the end you have to return to the base station, because the communication there could be communication problems. And the planner helped, or it's a fairy tale story. So if you put the breadcrumbs, you can return home, right? So that's similar to the poses of the robot, because you need the localization to report the artifacts. And if you know your trajectory, you can actually return from anywhere in the world. And it's independent of your exploring trajectory. So this was simple and worked very well. About the RGBD camera together with the 2D LiDAR, that was must-have in order to detect the down-drops and holes, vertical shafts with the elevator, etc. So that's kind of matched to the real world. Not perfectly though. Okay, so yeah, I'm sorry about this slide. I wrote it, I don't know, 3 months ago, when we really didn't know anything about what's going on, because it was you submit it, and then 3 weeks after you know the numbers. And that time I was a bit upset, but it's not really a waste of time. The simulator is like the level of the simulator for the tunnel circuit and the urban circuit is like 10 times bigger, or better, bigger too. In particular, like for the tunnel circuit, we had to write everything in the standard output, and it was the only output to get. So like we were, for example, counting messages we are receiving, just to check if we are really receiving. Now we can store up to 2 gigabyte log data, and then reprocess it or analyze it. So maybe I just like could sketch like how the work is done. We have 5 robots. Each one has 2 gigabyte space for recording the log files, and it takes about 5 hours to simulate these 5 robots because the simulator is slower than the reality. So like the daily business was we started simulation on 3 practice worlds. The next day we downloaded 3 times 3 practice worlds. So the next day we downloaded like 30 gigabytes of log files, analyze it, prepare a new release, and another day, another. We end up like 50 versions released, just to have an idea. Again, like if you want to have track and have fun with our code or laugh at us, check the GitHub Robotica. So that's the cycle. Environment is changing, but the robot configuration is frozen. That's kind of strange because like you would expect that in the real world it is harder than in virtual world. Here it was the opposite. Like if you don't like your mounting of the lidar, you just like unscrew it, put it down, and it's done. In this virtual world, you don't have option. It's just like off-the-shelf combination. It's slightly changed with this urban circuit, where there are like new configurations prepared and like pull requests available. And it seems that it will be like even better in the cave circuit, as guys from the Open Robotics took pictures and 3D models of the robot. So you may even see our Cloudback K2 in virtual world, which would be like great, and we would really be happy to support it. CloudSim upgrade one day before the end. Forget it. It was really good this time. They were announced the freezes dates, and it worked well for us, I would say. Qualification does reflect. That also changed because like you had qualification worlds, so like you are kind of prepared what to expect, but then the competition was like somewhere else. And I mean, like the sensors would not fit, and like you would have to really change the strategy completely. This time, one practice world, randomly picked, I don't know which one actually, was reused for like one of the 8 worlds. We'll see. I am looking forward to see the data. So again, like great. This was like checked and works. Limited support on the Amazon. That's something still not like good enough, I would say. You have this 5-hour simulation. You just trigger it in the evening when you go to bed, and in the morning you find out that the pods are still deleting or that it failed for some reason. So like you lose one day, and you cannot get to the log files like what was wrong. It doesn't have to be necessarily your fault. But again, like I think it's like going the right direction, that like the communication with the organizers or like the maintenance is improving. Black box evaluation, I think that's still true. I mean, like this time we didn't worry because like we could fully focus on the system track. But it's kind of pity because like you can watch the system running like every day. You can see like nice walking robots and drones, and like it's really like cool to watch it. But on virtual, all you have, I guess, is the numbers you see on the like leaderboard table. And I suppose there will be also like cool views, like I don't know, Kevin's flying with the drones, exploring 9 levels. I would really love to see it. Or even we experiment with the 5 robots, like just one robot following each other. When one fails, it actually creates kind of like this is dangerous area, so like next 4 will follow. So it's sometimes fun to watch. And yeah, so it's too black for me. If it's possible to like make it more visible or like what's going on, that would be great. Like one suggestion would be like really just to stream the simulation afterwards, because like now it's locked, you submit your solution and wait 3 weeks. Fatal failure. That's unfortunately still true. Even like you have seen the results, you see 100 something the first, 100 something the second, we got like 20 points. But if you check like in these 8 words, we just got points from 1 and 0, 0, 0, 0, 0, all others. So I guess there is some issue we will investigate and like discuss it later on. Again, like let's close the urban circuit, but we will really be happy to like support the solution for the cave circuit that I think like more competitors will enjoy too. Okay, lessons learned, is there? Oh, that's all. So if you have any question, or is it, please ask. Or I can talk more about like our solution. Like the organizers were kind of surprised that I have never seen the world. Like my typical work is that I connect to SSH, just terminal, to simulation machine. I start the simulator, I start the robot, I start the bridge. It does something for a while. It's something like sending the robot in the tunnel. When it returns, you download the log file, and then you analyze it, or you run some scripts which will analyze it for you. And the same was for this virtual world. Like you almost don't recognize the difference because you connect to the like virtual or real robot, download the log files, and then you analyze the log files if it worked. So, and it was kind of like fun because you don't know where are the artifacts, and you can see the improvement of your algorithms. Also, some people may ask if you use ROS or not. Well, if you want to compete in virtual world, you must use ROS because it's like ROS-based. But we really don't use it. So how to do it? So we have kind of hybrid system, and we use the hybrid system on like smaller robots, and in the end on all robots. That there is some proxy, and we use our Oscar, which logs the minimum data necessary like to control the program. And then there are the ROS data, which are big and like we are not able to log all of them. And it actually works fine. So like we live in both worlds, if anybody's interested. And yeah, and then like funny stuff, like also the Sodium was mentioning, the robots are red. The color is exactly the same as the backpack. So like once we got further with these 5 robots, like the most detected artifacts were the robots itself, which again, like the correct or easy solution which we missed was because it was like a Robotica model, we could paint it green or something. So, but it was too late. And the solution we did at the end was the combination of the RGBD camera, which is taking the 3D sizes, and that worked fine. Well, before I forget it again, I would like to thank DARPA for this incredible option to like participate here, both system and virtual. I would like to thank the team because it was really a pleasure to work with them. I don't know if it's a pleasure to work with me, but we survived. And definitely I would like to thank all the like families and other companies who support like the SIG, support us in this event, because it's not easy to do it all at once. Thank you very much. Any questions? Okay.
Please welcome to the stage CTU Kraz Norlab.
Okay, so hello everybody, Tomáš Svoboda speaking. And okay, so about us, okay, let's put it. So essentially 2 members of the team. One is Center for Robotics and Autonomous System from the Czech Technical University in Prague. And it's a kind of over-departmental configuration of researchers. So the researchers come from the 2 departments, computer science and cyber ethics, and the colleagues from Canada, Norlab from University Laval. And yeah, we've been doing robotics and machine perception, machine learning for quite a while. So for instance, we did a lot of in the image recognition and recognition in visual data in general in the past. Okay, about the technical solution, we adopted, like many other teams, we opted for several kinds of robots, like, you know, being ready for any kind of terrain you might expect. So we have the hexapod, the walking guy, the flying quadrotor. Most of the fleet consists of 3 tracked robots with, you know, this active flipping funny thing, and 1 husky, you know, the usual wheeled solution. So we hope that with this fleet we'll be able to climb, fly through any kind of environment in all the 3 tunnels. We are still hoping to get a new robot, but we'll see. It takes time, and you know, it's difficult. About the technology approach in detail, so yeah, many things. So we do have 3 kinds of wireless communication. Perhaps the most interesting is the in-house long-range small bandwidth communication. It did, at the end we use it, it did work at the end. Unfortunately, we still didn't manage to full integrate it, so we were not dropping nodes as we wanted. But still it proved usable because we were able to reach all of the robots just even without the nodes being dropped. For localization, we do LiDAR-based localization, which I some kind of call ICP on huge steroids, and it's mainly done by the colleagues from the University of Laval. For the local maps, we also include some RGB depth sensing in order to get more data, so we are fusing. And the local maps are stitched together by using the transformations that are coming from the localization node. Then the frontiers are found in favor to extend the known space as possible, and you know, the path is planned through the local occupancy map. The flippers that were mainly, for instance, used when going down the staircases, it's automatic. It essentially uses the inner state of the robot, so the speed and the inclination and so on, and the information from the robot surroundings. And it does not only the flipper, but it also controls the speed of the robot, and it essentially does the plan execution. So there's one node that does the flipper thing and the path execution at once. Actually, we did a little bit more sharing data in tunnel circuit than here. It was mainly because of lack of time. We were really struggling several weeks around Christmas to make our robots operational from the hardware point of view, so we were lacking the time. So we didn't really do any kind of multi-robot collaboration, unfortunately, in this tunnel circuit, in the urban circuit, and this is something we really want to do in the next round. So this is definitely for us future work. The mission plan, the mission procedure includes the human operator, And it's kind of the, as usual thing, it does the high-level decisions about whether to stop robot, whether to reinitialize something if needed, and so on. And we actually did a lot, we invested quite a lot of work in making the operator console quite efficient. We've been working on a project with firefighters, so we did quite a nice experience with real human rescuers. Of course, this console is not the same as for the rescuers, but definitely the experience with the real rescuers helped us to define the operator console as well. So it was not easy to work with the real users of the robot, but actually the lessons learned there is also helpful now. And I think that our team has several strengths, and one of it is definitely the kind of fault tolerance of our system. And it's not only fault tolerance to the software failures, but also to the hardware failures, right? Because the major part of our field is, you know, those tracked robots with the swaying gliders come and forth. It's quite old, 10 years old now. So, you know, motor drivers are dying, the flippers need to be restarted automatically on the mission and so on. And it's all, we have nodes watching the hardware, we have nodes watching other software nodes and nodes and so on. So we are pretty good at making, you know, the robots keep going until it flips back on the staircases or burns in flames. But aside this, we are quite capable of keeping it going. Okay, lessons learned. Initially, I had none, but the guys told me that I simply have to have some. Okay, so I collected. Okay, so actually, you know it, I think, pretty well. I mean, the full autonomy is nice, but inevitably leads to some strange robot motions, and inevitably the robot bounces, hits the wall occasionally. Actually, most of the robots are quite capable in surviving, so they survive, but to somewhat surprise, the mapping did not, at least in the first 2 days. So we worked overnight, so we improved the robustness of the mapping for the second 2 rounds, and we improved in the second 2 rounds, so it helped. But there's still definitely some work need to be done, so in the full autonomy to make the mapping more robust against the bouncing. Yeah, the robots are old, but actually knowing the robots very well has also advantages, but because if you need to fix them, then you know how. And you know, we are taking a lot of spare pieces with us, you know, so we are quite skilled in making the robots working again. We realized that we definitely need to have some efficient way of moving more robots to a distant place, so some kind of compact formation there, so not really leaving each robot alone, but it also goes back to the more sharing information about the robot and more using the shared information that we didn't do in that urban circuit. Okay, so I talked about the necessity of using the shared information. And yeah, we definitely will need vertical flying. I think the flying guys did quite well. The horizontal flights were quite long, several minutes, fully autonomous, but we still can't do vertical flying. And it's maybe because you know, we hope that the flying wing of our center will be more involved. Actually, nearly all the flying guys were in the MZ competition, winning the grand challenge there just 2 days ago. So we hope for more help for them. And if I may, I really enjoyed. I really loved to be among the young guys, you know. Like, I almost felt like back in my PhD times, you know, hacking the stuff, and it was really nice. I didn't hack the system, no. I just, you know, helped making breakfast for the guys and so on. But it was, so please allow me to express my joy by 2 funny items at the end. So one lesson learned is that definitely the UAVs are flammable, so we know well.
And those who remember the Pittsburgh problems we had, the beers are here much easier to be purchased in larger amounts than in Pennsylvania. So it is good on the Washington State that you can really buy beers without any problems. So yeah, so thank you for this nice event. Like really made me young again for at least a couple of days. Okay.
Please welcome to the stage from the virtual competition, Coordinated Robotics.
Good afternoon. My name's Kevin Knadler, and I'm talking about the virtual track for Coordinated Robotics this time. So for the virtual track, it's a much smaller team, just me. Has its trade-offs, has its benefits. The goal coming into the competition this time was to get the UAVs working and to get those UAVs coordinating and scoring points together. At the tunnel circuit, I did not achieve that, and so really wanted to push on that and get that to work. The technology we used is we used the quad rotors in there. They're called the X3 in there, and configuration 5 used an RGBD camera on the front. I also wanted to use the SSCI X4, which I earlier mentioned. It had a 3D LiDAR on it. I was not able to get the SLAM working with the LiDAR well enough in simulation to be able to use that vehicle. So as I mentioned, the key goal was to get those aerial vehicles working in the simulation. That was achieved. Localization, I used the RGBD SLAM plus some filtering to clean things up. Local planning, I basically used a 3D wall following approach. It had some obstacle awareness, so it didn't get stuck in funny corners and was able to return to base without getting confused, and so there was some helpfulness there. Global planning. During the tunnel circuit, I used a graph-based approach. As was mentioned earlier, the tunnel circuit lended itself well to a graph-based approach. You could use traditional search methods to go through the graph and find what you're looking for. The varied structures, the open spaces did not lend themselves as well to a graph-based approach in the urban circuit, and so was not able to get that implemented in time. In communications, the goal was to share artifacts and maps among the robots. I had been able to do that in the tunnel circuit using the graph-based approach. I was only able to share artifacts so that the robots did not repeat the artifacts. Basically used some randomization to send the robots out on different paths. 2 robots would go out at a time and then return after that. Slides change automatically, cool. Lessons learned at the urban circuit. As I mentioned earlier, it was difficult to adapt a graph-based methodology that had been used in the tunnel circuit to the urban circuit. Part of that was time-based. The virtual circuit last time basically lasted through roughly October, and so it was a November, December, January implementation time. And so that's a fairly tight squeeze for anything, and so I was happy to get stuff working. The OSRF folks, or the Open Robotics folks, made the environment much more stable this time. Just numerically, there were approximately 90 issues submitted over the same time frame for the urban circuit compared to the tunnel circuit, and even more so than that, the environment was a lot more stable this time. The UAVs worked in Cloud Sim. Somebody working with Open Robotics implemented a controller that made the UAVs much more controllable, and so that was a huge benefit and a nice piece of work they did. Cloud Sim still had issues in the last couple weeks. When there's lots of people using it at the same time, you get funny behaviors, and so some more work to be done there, but overall the environment was a lot more stable. Let's see, other lessons learned. Those are the main ones. I have a fairly short talk this time, so we'll get done quicker. Any questions? Well, I just want to say thank you to DARPA and thank you to Open Robotics for all the work. I know there's a lot of work that went into this, and I appreciate it.
Please welcome to the stage, Explorer.
Hi, everybody. First, I'd like to thank CTU Cross NOLAB for lending us their total station in the most critical moment. And then also of course, the team who put in a lot of work over the last couple of months since August, and I want to show you some of these things. So since the tunnel circuit, our vehicles were much larger, and that was on purpose. We wanted to focus on smaller vehicles for the urban circuit. So the team that we have is Carnegie Mellon, Oregon State University, and we have a set of sponsors. At Carnegie Mellon, we are focusing on the hardware, the perception stack testing, and then the software coordination and object detection is at Oregon State. You can also see it here. Okay. So this is our fleet of robots. So you can see we have 3 ground robots. You can see a different set of wheels on the smaller platform. We have actually, I'll show you some of this. We've gone through a lot of iterations for this. And then our drone. So the robots are called R1, R2, R3, and the drones are called DS1, DS2, DS3, DS4. And actually, what we really wanted to have is R2D2. So that was kind of part of the goal. But we didn't quite end up in the naming like this. You can also see some of our test site that we used for the urban circuit. That is an abandoned hospital in Pittsburgh. It's probably, yeah, I would say maybe it's larger than SATSOP, but it's different in terms of the distribution, and I think that is, and the environment, and I think that caused us some issues in the competition in that it was much more hallway, tunnel-like than these wider open spaces that we expected. Here you can see us going up a set of stairs with R3, so you can also kind of see actually the stairs are quite similar, but I guess different enough that it wouldn't work as well here. Let's see. If there's an audio in the video, it might make sense to mute it, or maybe not, I don't know. So here you can see the vehicle exploring. We have the perception pillar on the top. There's a landing pad. This is kind of our test place here. Let's see. You can see the communication nodes we have at the bottom. This is Matt Travis, my co-lead. Can't quite hear what he's saying right now. This is our operator. So the drones take off from the back of the ground robots, align themselves with the coordinate system, and then go off explore. And let's see. So you can kind of see us kicking up some dust. Let's see, what else is there to show here? So the stack on the ground robots and the drones is quite similar. So we have essentially a Velodyne, real-sense cameras. We have some thermal cameras on the drones, and we've been able to go down these. So this rope is just purely for safety. This is not part of the strategy. And I think something that might have not been apparent in the video feed was we actually managed a full loop down the stairs and land on the wheels. And the robot was still in one piece. So I think, oh well, 2 pieces. Just the landing pad came off. So on a very high level, these kind of 2 approaches we have is one, this idea of modular autonomy, and the second one is this resilience. And so you can see in terms of the autonomous system, and you can see a little bit of that in some of the behaviors in the stream as well. For example, one time the ground robot got stuck on top of we call it the robot trap, basically these 6x6 frames. And I think we also saw Costa, I think, getting stuck on those. Basically, the robot eventually kind of gets itself out of that situation. In some of the drones flights, you can also see this, where, for example, the robot will go somewhere and then it will say, hey, oh, something's wrong, it will back up. So that's kind of part of that behavior. Some of the lessons learned at the urban circuit is, I think part of our testing wasn't quite as good. Maybe we didn't quite expect these kinds of objects. You know, the tunnel, a lot of the objects were closer in, here they were further away. So I think that affected us also in terms of exploration strategy. That's something we'll definitely look at. I think the test site was awesome. It was really nice, and you could really imagine how you could be in such a situation. Some of the things that worked quite well is our deployment of the different robots. We had about 5 robots on course. Our new communication system, I think, worked also much better than expected before. So that's kind of it. I think I think there's still plenty of time if people are interested in any aspect. Any questions? Okay. Oh, Kostas, yes.
Thank you, Basti. Very good work, of course. But can you share more about your resilience techniques? Is it all prescribed? Is it something that is searched within a local space? Or
So I think the idea on the high level is to have kind of an executive that has some objectives of the overall system, and then you have many different methods in parallel that are running, and you try to choose the best method possible. And so it might be random, it might completely turn off perception, do something blind. It might be, there's many different potential behaviors you could have, but which behavior is best is not clear up front. It depends on the environment, and trying to do that up front is tricky, right?
Hi, I remember in one of the interviews after the run, you mentioned that there's something happened to the artifact detection. Could you talk about a little more?
So I guess objects are detected on the robot, and somehow that information has to get back to the base station. And so in that pipeline, so there's the main thing that happened was that often a lot of things didn't get back to the base station. They basically got stuck on the robot. Sometimes we didn't get close enough to objects to be able to detect them. I think those were the 2 main failures we saw. Any other questions? No? Okay, thanks.
Please welcome to the stage, Barks.
Yeah, hi everyone. I am Meryl Spencer, and I am here representing my team, Barks. We are out of MTRI, which is an independent research center for Michigan Tech University, and we are located in Ann Arbor, Michigan. We are a PI-driven institute. So we do lots of different work, but some of the main things that our PIs are interested in is signal processing, remote sensing, autonomy, obviously AI and machine learning, some statistics, and sensor systems. And we apply those across a really wide variety of domains. For the urban circuit, we had some new challenges coming out of the tunnel circuit, first of all, we had some new falling hazards. Oh, I don't know why it wants to go forward. There we go. So some new falling hazards, such as the stairs and the platforms. As some of the other people have mentioned, we are also using a graph-based search strategy, and so we had to do quite a bit to change that to work for searching in open spaces. The new artifacts to detect, some new traversability challenges, especially around the subway tracks, which we'll talk a little bit more about later, and some localization challenges. And I'm the only one here today, but unlike some of our other virtual competitors, this is not a team of one. There are many other people on the team. I really want to call out especially Sarah Kitchen, who is our PI for this program, and Reed Sattel, who has done a really great deal of the work for getting this all up and running. So for our urban team, we decided to go with 2 X1s and 1 X2, and I'll sort of talk about some of the reasons behind that. So first of all, backing up a little bit, our main goal on BARCS is to develop a core controller that has sort of minimal sensor assumptions to it. So our goal is to create one controller that we can use with hopefully only a little bit of tweaking to run on many different platforms. So we are doing a graph-based search strategy, so our robots are generating a graphical representation of their environment that they can share and merge and hopefully be understood and navigate as the heterogeneous team. We're also using a graph representation to do our frontier search. I'll talk a little bit more about that in a moment. And we decided to go with the long-range LiDAR and the HD cameras for our team. So getting into some more of the specifics, we're using Google Cartographer for SLAM. Especially in the urban environment, we ran into a lot of issues with these very, very long, somewhat featureless sort of subway tracks, and having the SLAM sort of start to have an unacceptable amount of drift. So that's something that we spent a lot of time tuning parameters for, and it's something that ended up working well, but I feel like that's still a challenge for us going forward, something we're interested in maybe coming up with a better solution. We're using a modified move base to improve our obstacle avoidance and increase our navigation speed. And along with that, we have some custom cost maps to provide some desirable behaviors. So for example, some of the larger robots can flip over if they run down the ramps too quickly. So that's built into our cost map. We have 2 different types of navigation behavior. So when the robots are in places that they've been before, they're using their previous built-up graph to do navigation. So they're doing just simple shortest paths navigation. And then when they enter new spaces that they haven't seen before, they're generating a graph of their frontier. So I'll talk a little bit more about that. So you can see some pictures of these graphs being generated. As some of the competitors have talked about, the open spaces makes doing a graph-based search a little bit more interesting. So what we're doing is we are using our 3D point cloud LiDAR data to create a graph that focuses on going through the center of an open space out to far off points. And so as you can see, our frontier graph is shown in red here. What you get is kind of this spider webbing coming out from the robot. And with that, then we're able to sort of rank far out frontiers in terms of how accessible and how safe we think they are and prioritize where we're gonna search. So one of the problems in this is, of course, getting blacklisting correctly. So we'll place frontiers over obstacles such as stairs, and we need to be sure to mark those as unsafe areas so that we don't end up just falling downstairs. Another issue that we have with this is distinguishing between when we're not receiving sensor data because there's really some sort of hazard, such as, there's no floor, or we've entered some sort of pit space in front of us, and when we're not receiving data just because there's some sort of temporary lag if we have computational overload for a moment. So filtering out that bad data from data that's saying, hey, there's genuinely a harmful area in front of you, watch out, was one of our issues. So for the urban track, we had some new hazards and obstacles for our robots to avoid. There were 3 main ones that we focused on, the first of which is the actual subway tracks themselves. The smaller ground vehicles had small enough wheels that they could get sort of wedged in the track, and that's why we ended up going with the larger ground vehicles. We had enough money left over to buy a small vehicle that was sort of sacrificial. So I'm interested to get the data back and see how many times it sort of went out and just got stuck. We're sort of expecting that might have happened quite frequently. Another problem is that the UGVs cannot reliably navigate stairs. You can, in fact, drive the larger ones downstairs if you're careful, but we didn't want to risk that. So we decided to just mark all stairs as sort of impassable terrain. And we did that by using the same neural network that is running off of the camera data to do our artifact detection. Also, we can have the UGVs just fall off the side of these subway platforms, which we happened to catch a screenshot of that in action here, of our little guy falling off the subway platform. And something that we chose not to do is we chose not to equip a downward pointing point LiDAR that you could use to assess whether or not there's a hole in front of the robot. And because of that decision, what we had to do was sort of fuse the camera data with the LiDAR data to do obstacle detection for the sides of the platforms. And so what we did is we looked for the yellow strip on the platform and fused that with some extra LiDAR information to do hazard detection for falling off platforms. And I'll talk a little bit more about that in a moment, because it led to some kind of funny behavior. So finally, obviously, our goal at the end of the day is to detect a bunch of artifacts, localize them correctly, and report back. And so there were 2 different sort of artifact types in urban. We had a gas vent. That was actually pretty straightforward. We were able to detect that via the sensors that we had on board. All of the other artifacts were detected through a neural net running off of our camera, and we also did a little bit of clustering after that to remove some false positives. One issue that we had with our neural net is actually that it was a bit too good. We were able to see objects even at an incredible distance. So I promise, even though it does not look like there is anything there, there is in fact a backpack down there that we have correctly identified, but we had to do some artificial cutting off on distances because we would see objects very far away, correctly ID them, but then localize them poorly. Also, just some amusing behavior that happened for our solution because we were using a yellow detector to detect the edge of the platform. Some earlier versions of our solution, our robots were very frightened of the yellow trash cans, and also there's a little yellow strip on the cell phone. So that led to some sort of funny behaviors. And so before I do lessons learned, I just wanted to take a moment to really thank everyone, especially Tim and DARPA for hosting this competition, and OSRF, who's been doing tons of great work behind the scenes, doing the integration and getting us a virtual world to go play in. And obviously, all of you are wonderful competitors. It was really great to be able to meet all of the systems folk in person. So I guess for lessons learned, probably the biggest lesson learned we had that is really sort of a continuation from the tunnel circuit is to test early and often in the cloud, as many people have said. We were actually able to do that really successfully for this circuit, and I think that was what helped us a lot. We got a lot of throughput, especially with, as people have said, some of these upgrades to the Amazon Web Services that let us do a lot more batch processing. We were really able to take advantage of that. So we did a lot of early testing of our solution in the cloud. And that's something we hope to keep doing going forward as we try and sort of narrow down on a better and better team, being able to run all these big batches of solutions and evaluate them as they come back. Any questions? All right, thank you.
Please welcome to the stage, CoStar.
Hello everyone, my name is Ali Aga. I'm team lead for CoStar. I want to first start by thanking SubTv team, DARPA team, for this amazing opportunity, and it has been really a lot of fun, being at this part of this event with all these wonderful teams, and we collaborate with many of the other teams even beyond this, 1 week. Mainly, I want to thank for the support from Cerberus, Cyro, and Marble teams that we work with them beyond this and write papers and so on. So it has been a wonderful opportunity, the whole event for us. Then I would like to also thank NASA, JPL's support, and our sponsor industry partners that has been very supportive. In particular, Boston Dynamics. They supported us a lot in the last 2 months. That has been an amazing collaboration. So our team is a collaboration between NASA's JPL, MIT, Caltech, KAIST, and LTU from Sweden. I want to also thank the members from these institutions and that has been working really, really hard for the last few months. I've been super lucky to work with this team. And one of my main jobs is I just tell them, slow down, guys. So that's a really good position to be for a lead. So thank you. So in terms of concept of operations, we rely on, like many other teams, on a heterogeneous team of robots with complementary capabilities. At the beginning of the course, we try to drop these communication nodes like breadcrumbs to create a wireless mesh network backbone. And once robots leave that area, leave the communication, contact with the human supervisor, we rely on autonomy and try to have some timeouts, some other conditions based on number of artifacts they found, whatever they have mapped, the amount of data they have collected, to come back and basically communicate the data back to other robots or base station. Here you see some of our robots that we have been developing throughout in the last year and a half. The robots in the top, except the one that in the very right in vertical shaft, was the robots that we took to the tunnel competition. There were a lot of robots. We deployed only Huskies, the fast data mule you see, and one of our drones, the small fast data mule. And in the Sticks event, we deployed some of the rollercopters, but not in tunnel. As we went to the urban competition, we tried to focus on a smaller number of robots and focus more on the software side and autonomy. And we mainly started, create a group around the Telemax robot, the one you see in the middle, the tracked robot. So we had successful stair climbing, going down capability with Telemax. It's an amazing robot. And in about several weeks ago, we got the spots from Boston Dynamics. So we started to integrate our frame payload on the spots. And I'm really proud of our hardware system that had such a modular framework that in a few weeks they were able to create a version of our Husky payload on the spot and allow the software team to play games with it and learn how to work with it. So in the urban competition, we deployed Huskies and the Spot. We were also ready to deploy the Telemax, but the environment, the Spot was successfully climbing the stairs and going up and down. So we tried to limit the cognitive load on our operator so that he can make better decisions by controlling maybe less robots. So in the maximum, this round in urban, we had 4 robots simultaneously operating in the mission. In urban, we had 5 robots in one time step operating in the maximum. So that was kind of the robots, the body of the system. In terms of the computing, the autonomy, we are leveraging a framework that is being developed in NASA's JPL called Nebula. It's an autonomy framework to handle unknown environments. It's beyond SubTv. Its main customer is DARPA Subterranean Challenge, but it's being mainly developed for potential future planetary cave explorations. Right now, there's a lot of focus on moon, and lunar caves are important potential shelter for future astronauts. That's one of the strategic directions, as well as if there is life in solar system, Martian caves and in general caves are one of the most likely places to find life because they harbor potential life from cosmic rays, and they have a stable temperature and so on. So in NASA strategic plans, caves are very important, and there's an effort to develop autonomy frameworks, which is helping us to be more prepared for the DARPA Subterranean Challenge. So in short, the Nebula kind of has 6 thrusts to it. So I'll go from top, in clockwise direction. There's a focus on modularity, as you saw. The speed that we were able to go from the Huskies to Spot was thanks to how modular the framework is and allows us to get pieces that are required and then put it on a new system and make it more autonomous. Navigation is another aspect of it, where in SubTv we rely on a fusion of various sensors based on uncertainty. We look at different signals come in, try to quantify errors and so on, and try to make it seamless for robots so the robot doesn't feel we switch from thermal to vision, from vision to LiDAR and so on, based on how degraded each channel become at various parts of the course. Mapping, of course, is a big challenge here, and also for Nebula. We are pushing our framework for mapping is based on PoseGraph. We create PoseGraphs at different robots, try to merge them. At this point, with our capabilities, we try to merge them in a centralized manner at base station, but we are hoping that as we move forward, we do extend this to a decentralized mapping. Mesh networking, of course, is the 4th thrust for us that is around creating a wireless mesh network with mobile node on robots and the ones that we drop like breadcrumbs. Task allocation autonomy is the 5th thrust of the framework, and machine learning and artifact detection is the last thrust of the Nebula, which in SubTv we are looking for artifacts and man-made objects. In space applications, we are looking at interesting science. We get the data from scientists that they label them on cave walls and say, okay, this is an interesting science or so on, and then we try to learn and give them suggestions that, okay, the robot has explored this much, these are interesting, maybe scientists need to focus more on that. With that broad overview, lessons learned, I think the first lesson we learned is bring a warm jacket. So that was an interesting challenge for many of the team members coming from LA, Southern California. And rice cooker also is useful when you're at ELMA. We had some interesting, events that in last minute our com dropper broke and so on. So of course, one of the main, again, lessons is try to stick to the hardware that you have. Don't make the very final changes, especially when it comes to hardware, and make the hardware more and more resilient. I'm sure many of us have experienced that. I think, but the biggest lesson is, which is ironic and interesting compared to tunnel, is at tunnel, I think biggest lesson for us was, okay, test, you know, take the robot to the field and keep testing, make sure everything is working and so on. That's still true, but we feel as the systems, we are getting to a kind of a baseline solution, systems are getting more resilient, it's kind of is looping back to theory. Now to push for more points, it looks like we need to go back and go really deep in research and make sure we handle the theoretical problems. And that's what we are very excited about it. So we are hoping the systems stay resilient. Our hardware team continues this incredible job and allows us to push more on research, because now we are seeing situations that you close a loop and now you have the graph for planning that is connected to your post-graph estimation. But now that you have closed the loop, your constraints on the map and collision checked, now where are your frontiers? You had a bunch of frontiers that you have stored to allocate between robots. Now the loop closed, environment has changed. Some of frontiers is under environment on obstacles, some are not. And just handling how uncertainty in different hypotheses, discrete in terms of what loop you close, what are outliers, and also continuous in the level of what are the grid levels in the obstacles, interact with these is very important. And in general, taking uncertainty into account and bridging the gap between modules, this is where we feel our system stopped. If we had this, we would have performed better. There are different modules, but module A doesn't fully take into account imperfect aspects of module B. So they're being developed in an isolated manner. If other modules work ideally, this module A is working great, but once they break, it's important to know how module A reacts to how sensitive it is to the failures in other modules. And that causes us to start thinking how to formulate problems on the edges, rather than working on these modules, look at the edges and formulate the problem on the edge, and a priori take those kind of imperfect behaviors into account in the design phase. So that's the goal for us moving forward. We think we are going to come back with a more risky approach in CAVE and on the theory side. With that, I think I covered all my points. Maybe the other lesson that I didn't cover is, as Kostas mentioned, we learned search behavior is missing for us. So we have been pushing a lot on traversability and coverage. And we did cover a good amount of ground in this competition. We were happy with that. But what we didn't do enough was we assumed, like tunnel, if we are at somewhere, we are going to see the artifacts. That definitely was not the case, as you probably saw in our scoring. We were at like 7 sectors we had covered, we had to score 1 in many cases. So we had to come back, take the robots back, or operators start looking more and reduce the confidence level on artifact selection to say, oh, okay, I see something here, and start scoring more. So we definitely need to work more on the search behavior and what derives the autonomy framework. And with that, I think I covered all my points. I'm ready for your questions.
Hey, Ali, congratulations on your team. Well done. I just wanted to ask you about your hybrid platforms. And so I know in the last 2 competitions you haven't deployed many of those. Do you anticipate deploying those in CAVE? And how is that development going?
We love those platforms, and we really want to deploy them. We did deploy them at the sticks, and we have played a lot with them in the first year of competition in mines, in gold mines near San Diego. We had to make some strategic decisions based on our resources, number of people we have, and our assumptions of the course. So we thought going up and down the stairs is going to be more reliable with Telemax first, and then when we had the spot, with a spot as well. So we didn't have enough resources to push for rollercopters. We are For moving forward for cave, we assume flight is going to be more important. So we already kind of have decided, like 5 of our team members that were working on ground robots are going to shift their attention to flight. So we are going to push. I am not sure we are going to go with rollercopters or just pure flying. We'll wait for DARPA's teaser video. I think every time we see the teaser video, the whole ConOps for us changes. So before the teaser video, we were like assuming, oh, this is gonna be a subway, we're gonna go down, and then we were thinking of platforms and railroads and so on. I'm sure many of you have like negative obstacles. We saw the video, so oh, this is nothing like we assumed. So we had to change many, many things. So I think so. We definitely are going to push for flight. If it's going to be rollercopter or pure flight, we will wait for that teaser video. If there are flat grounds, we'll definitely try to go with rollercopter. Any other questions?
Hi, I had one question. I'm surprised that you said that you don't feel like you needed to do more testing, and I feel like there's a lot of sentiment from other teams. So I'm wondering, what's the secret, and from your perspective, where did you test, and how did you test?
Yeah, so no, testing is absolutely most important. I think in tunnel, the lesson learned was we had not done enough, or we had to do, we learned that testing is important and we have to do testing and so on. And we tried to embed that into our, framework. So we were pushing ourselves to continuously test and create these games that I was DARPA and the team was, I was taking the clock, So we were continuously trying to stay in the game mode and so on. And we're trying to take it be very strict on that, because it's super easy to say, oh, we need to do a little bit more development before next game. But we had a good cadence on that. So I think we kind of doing okay on that cadence. We should try to definitely preserve that. That's difficult, to maintain that cadence. But I think once you have that cadence and you're trying to test continuously, then the next question is how to improve further. I think at least us, I think the barrier we are hitting now is the state of the art is not enough. So we just have to push, right? So there are not enough accurate enough SLAM solutions out there in the literature, or there's not a perception-aware planning out there, right? So there are amazing planning frameworks, but they assume your state estimation has spit out through a state, and the map is there. So, but now this competition is really pushing this holistic view, right? So we have to solve this at the same time, and that interaction, to me, it kind of creates a new science. So like, I don't know how many years down the road, but someday, 10 years, 20 years down the road, like control theory, communication theory, I'm assuming there's going to be an autonomy theory. So I think that's going to be, so that those interactions, new frameworks that can look at these different modules at the same time, I feel will create that mathematical backbone for those. That's what I'm talking, that, for moving forward, we are trying to, come with the competition with a little bit more different theoretical framework, and which is going to be risky, but we would like to do that.
Thank you.
Any other questions? And in general, I mean, like I said, we are working with other teams, Cerberus, Cyro, Marble. We would love to work with, we would love to share all we are working on and learn from you. So I think this is a great event to create these collaborations. So if any questions, please come talk to us.
All right, thank you, everybody. Well, first off, let me say thank you so much for taking the time to learn from one another and to share the insights that you've gleaned, not just from Urban Circuit, but also your time from Tunnel Circuit and moving forward. There were a couple of really interesting technical nuggets that I was digesting, taking my notes as well, and a lot of them revolved around a couple of key points. And so if I may, I'm going to summarize what I heard from the technical interchange meeting. Some of the key aspects that came up were these notions of the role of heterogeneity in your team. So what's the right type of robot? What's the right type of sensor to address the right type of problem that you might face in these unknown environments. So I thought that was an interesting aspect of how you would balance or optimize how you design the team to best fit the environment at hand. The second was the notion of the environment itself. So there were a lot of questions about the assumptions made about the environment and the impact that that had in your design process, as you might imagine. And so the question there for you all is, do we have a firm understanding of the impact of the type of environment on your strategy or the algorithms or your robot deployments? So what do I mean by that? Well, if you found out immediately that the area is wide open space, do we have a good understanding of how that's going to change my robot lineup? Do I know that that means I have to plus up my air and decrease my bigs or something like that? And so now we're starting to get a sense. We had 2 events so far, tunnel and urban. That's typically enough to at least do a very coarse gradient estimate. And now we might be able to start understanding what it means when you have confined spaces versus big open spaces, when you have long topologies, sparse topologies versus dense topologies. What does that mean for designing the team that can conquer these really complex environments? And then the third bullet, of course, is going to be in the notion of communications and coordination. So again, how do we strategize about what to communicate, when to communicate, how much to communicate, and for what purpose? Is it for exploration or is it for search? So I really loved all of those being touched upon. I think the whole takeaway here is we in this community, and I call us a community, are able to now think about the problems in a derivative sense, in a gradient sense, not just let's solve the problem for tunnel or solve the problem for urban, but let's solve the problem of subterranean robotics so that we can understand, hey, this piece impacts that and have a firmer understanding. And let's go out and test and break things at the same time so we continue to learn. So I really appreciate everybody sharing those types of lessons. I think the lessons, whether they're from near or far, from tunnel or urban, are incredibly valuable. And I look forward to all of you continuing to share and being able to learn from one another and beyond. So thank you again, everyone. And so to that end, one of the things I'd like to highlight in closing this segment of our technical interchange meeting is the idea that we have a lot of data products that DARPA has collected, and we are immediately prepared to release all of these. Part of that, of course, may have to do with some unnamed looming conference paper deadlines that might be right around the corner. Some of you may be targeting, but ultimately here are the things that are ready to go and available for you to go ahead and make use of. We have our virtual testbed repo that we've talked about in the community, in the virtual competition, with all of the robot platforms and the new additional ones that are now ready to go with our latest and greatest for the virtual competition. And so for those who are virtual competitors, your logs are ready for you to download, enjoy, study, laugh, whatever you'd like to do with your logs, but they're ready to go. And those competition worlds that I presented earlier today are available for you to take a look at, inspect, and even start doing additional testing in as well. We have all of the ground truth artifacts as well as those fiducials that were placed on the course for configuration 1 and 2. They are present in that spreadsheet there for you to go and assess the quality of your reporting, and you can do your own kind of post-game analysis, if you will, of how close your artifacts were and some of the errors that were done there. So those are ready for you to go. The map data is also available. This is the ground truth map data. This is the scan. This is subsampled point cloud scan of the SATSOP center. All 3 of those levels are available, again, for you to make use of in your own analyses. We've gone ahead and also, for your viewing enjoyment, generated these point cloud fly-through videos. These allow for you to just go and fly through and get a sense of what that ground truth point cloud data set that we've collected, so you can become more familiar with the site. And also, that's the graphic that you see there on the right-hand side there. It'll help facilitate. For those of your teammates or friends or family who wish they could have gone on that course walking tour, we've gone ahead and videotaped that course walking tour, and not just for both courses in configuration 2, like you walked, but in fact, we did a walking tour for configuration 1 as well. and we're inspecting each and every one of the artifacts along this video walking tour. So that's available for you to take a look at, so you can also get a better sense of what, how configuration 1 and configuration 2 was available for you. And then finally, for those of you who had a chance to take a look outside with the immersive environment that we were able to do a scan, those Matterport scans, you can go to a web browser to take a look, or use your favorite Google Cardboard viewer if you wish. But those are also available for you to have a little bit more of an immersive experience, and so you can kind of look around and see what that whole world looks like from within using that Matterport scan. So the key takeaway here is this competition is not just about competition, it's in fact also about collaboration and building out that community. You'll see announcements of these released data products on our SubT community forum, but at the end of the day, it's about sharing this type of data so that you can continually accelerate. And my hope for all of you, to those who are willing and able to do so, go ahead and feel free to share your logs, your maps, your pictures, your videos, and things of that nature, because that'll undoubtedly help one another as well. And so with that, I'm pleased and proud to conclude the urban circuit in general. I think we've had many lessons learned. I think there'll be some really great trend lines going towards cave circuit as well. And to conclude and close out, I'm pleased to invite Dr. Tom Beutner, who will give our closing remarks for the urban circuit. Thank you.
I'm Tom Beutner from Tactical Technology Office. I'm Deputy Director there. And I just can't tell you how impressed I am by what I saw over the last few days. The amount of work that goes into fielding one of these robotic teams is truly impressive. Navigation, a level of autonomy, HMI, networks and comms, but we certainly had no idea what the optimal solution would look like, and that's where challenges at DARPA often play. Challenges are great when we understand the problem, but we don't know how to solve it. We certainly don't know what the optimal solution looks like. And so these are oftentimes a way to explore a design space that we can't do any other way very easily. And you've all been part of that exploration, not only figuring out how to get through these mazes that Tim has devised, but also thinking about, in more general terms, how to approach these problems. And this diversity of circuits that we're doing also is part of that dimension. And the 6-month timing is no accident. You have to go into this very aggressively, and you have to take solutions with you that you're going to carry into the next circuit as well. DARPA challenges also oftentimes create a step change in technologies and in the applications of technologies that are already off the shelf. They also oftentimes create a community, and I'm pleased that I've seen both of these over the last couple of days. Certainly some innovation in the solution space, dealing with the complexity of the spatial environment, the multiple levels, verticality, stairs, and other obstacles that were unique to this course, but also the camaraderie both within teams and across the teams. You could see it all day today as people were talking about their experience here, people sharing ideas, sharing tools. I suspect that for the students that were involved here especially, you will someday look back on this as a pivotal point in your career and an opportunity for learning that would have been hard to accomplish any other way. But you're also likely to cross paths with the people in this room multiple times over your career as well. This is part of a community that is helping to define the state of the art as we move forward in this kind of an autonomy application. I would be remiss if I didn't take a moment here to recognize the tremendous effort from Tim and his team. While you were all working on ways to solve these autonomy challenges, they were trying to create them for you. The amount of planning and coordination that goes into one of these events and the prepping and execution of these challenges is incredible. And it's taken a large team of hand-picked people who were really dedicated, put in countless hours to doing this. The thing about challenges that's unique is the amount of effort and planning that has to go into them. And most people, when they run a challenge event, it's a once-in-a-lifetime opportunity, meaning that they don't get a chance to do it again, and they wouldn't want to if they had that chance. What Tim has taken on is doing multiple challenge events and doing them on 6-month centers. That is incredibly difficult. And there's also an aspect of this of devising a challenge that is kind of a Goldilocks problem that's just right. Defining the technology state of the art in a way that we can then challenge it, try and create that step change in what we're able to do without making the problem impossible. That takes an incredible attention to detail and a lot of planning, both in the design of the circuit as well as in the way that it was instrumented. So I'd like to take a moment. Many of Tim's team, I think, are actually back there stripping out wires and sensors. But for those that are here, and I think Alyssa is in the back room if she wants to come in. For the members of Tim's team that are here, please stand up and please join me in thanking them for all their efforts. So autonomous systems, the kind of robotics that you're fielding, have long been a vision for the R&D community. They've been something that has been promised for decades, and we're recognizing the potential of those systems already in very specific applications and in specific domains. But there's so much more to come. And all of the people in this room are helping to define the state of the art and to advance it as we go forward. Hopefully for all of the teams that were here, this was a forcing function to generate an integrated solution, and there's nothing like a deadline and a real test to give a sobering and stark assessment of what we can really do. But I hope this was also an opportunity to test your approaches and your systems in a realistic environment, and that you can leave here today with some of the lessons learned from that that may be applied to the cave circuit in a few months. But as well that you walk away from this with a sense of pride in having been part of a challenge that is advancing the state of the art, and that is eventually going to be critical in saving lives and protecting the safety of first responders and other people who work in dangerous and complex environments as well. I look forward to seeing all of you, or most of you, in 6 months in a cave. I want to thank you all for participating in the challenge and for sharing your insights today. I hope that this was as positive an event for all of you as it was for those of us who helped to organize it and plan it. Thanks again.